realm of superficiality and take the big picture in.
What is the story that we're picking back up on, Randall?
Oh, it's the story of stories. It's the story, let's see here. It is the story that the Ice Age Floods Institute, let me show you this here, and when you ask me about the story, we'll get right into here with some sharing. How about that?
That sounds great. That sounds great.
I'm going to share because, you know, I like to share.
So if you're just tuning in now, we are picking up where we left off on the last episode, and this is the story, possibly the greatest story yet untold.
Now, I have modified, this is the tagline of the Ice Age Floods Institute, right, which formed pretty much, I think, back in the 90s, because the first time I went on an exploratory expedition in search of knowledge and direct experience of giant flood-created landscapes, I visited the Ice Age Floods Institute in Washington State, in the town of Moses Lake. And it was one office with one little old lady sitting in the back of the local Better Business Bureau of Moses Lake. And I think there was a few chapters at that point, but what was this, 97 or 98? 98. It was 1998. Well, now there's a couple of dozen chapters all over the Pacific Northwest who are very interested, you know, even obsessed with this story, because as it's unfolding, it just gets more interesting, more complicated, more profound. And so I've modified their tagline to say this.
Big is instead of maybe.
It is. Well, one reason it is the greatest story yet untold is because it is so far-reaching in its implications to a lot of other things as well. Let's look at it this way. If we were going to try to come up with an authentic history of the human race on planet Earth, and we completely neglected an event that almost exterminated, almost resulted in the extinction of the human species, that would probably be a critical oversight. Wouldn't you agree?
I would agree.
Yes. And if the recovery from that event or series of events was fundamental to understanding the rise of history itself, then we would even further deem that to be of critical importance and value, wouldn't we?
Yes, we would.
And I think we can make that case that it is, in fact, the fundamental substrate of the whole of the last 10 to 12,000 years of the human experience on Earth. And that the events that went down that are being referred to here, see, and here's the thing. I'll deviate for a second. You'll see in a slide here in a second what I think is very symbolical of the constriction of the thinking that has surrounded this particular event. So we'll just dive right into it. All over the North American continent are to be found an assortment of features that are difficult, if not impossible, to explain by reference to modern, currently observable processes, and when they are taken as a whole, implicate the action of events so extraordinary that they almost defy comprehension. It is our judgment that the full mind-bending story of these events has yet to be told, and that when told, it will alter forever our understanding of both the history of the world and of humankind. That's a lot to live up to, but I think the story does live up to that. We will give homage to some of the founding fathers of understanding modern catastrophism, modern diluvialism, after it had been thoroughly discredited, thoroughly denounced by the mainstream of geological study. So this is what he said when this let's see, when did he die? He died in the 80s. He was 96 years old. Ideas without precedent are generally looked upon with disfavor, and men are shocked if their conceptions of an orderly world are challenged. And he was 100% right on there. J. Harlan Bretz. Notice his first name is just the letter J. I'm always getting corrected. You forgot to put the period after J. And then I say, no, it's not an abbreviation. That's his first name, the letter J. Okay? Anyways, J patiently taught us that catastrophic floods may sometimes play a role in nature's unfolding drama. And we saw in this last episode, we went through some evidence for one of those great floods. One of those great floods. And we ended with looking at a site at the border of Idaho and Washington. And at this site, two of the greatest, most spectacular and catastrophic floods in the history of North America met and intermingled. Now, it's going to take some time to sort that out, but that's tremendously significant. Why? Because under current models, the Great Bonneville flood and the Great Missoula flood just happened to be incidentally related because they both occurred sometime at the last ice age, but they both had totally different causes and were unrelated to each other. That is the conventional thinking about these two floods. I, on the other hand, would argue that they are intimately related to each other and that they were even happening concurrently. And if they were happening concurrently, then we're faced with the fact of explaining that away. Well, that's merely a coincidence that they were happening at the same time from independent causes, not that they were happening at the same time because they were both results of the same cause. See?
Yeah, we're having to stack up a lot of coincidence to be able to believe the mainstream narrative.
So if we make that transition, that transcendence from two separate unrelated causes to one greater overriding cause, well, what that then does is it imposes upon us the necessity of expanding our thinking. And I'm going to argue we have to expand our thinking enormously by at least a couple of orders of magnitude. There's the man himself, J. Harlan Bretz, with the University of Chicago, and he was the discoverer of the so-called Missoula flood, circa 1923, through his studies of the channel scabland of Washington. No, actually, this would have been later. I'm looking at his age here. He's in his 60s, so this was probably in the 50s, late 50s, that he would have been about that age. His name for the event was the Spokane flood, and I'm going to actually propose this. It's usually now known as the Missoula flood, after the town of Missoula in Missoula, Montana. And you'll see some photographs here in a minute of the evidence of the presence of a gigantic volume of water in the Missoula Basin, where the town is now located. I am going to suggest, and if anybody who follows me through this whole chain of logic and evidence that I would be presenting will understand why I think we need to actually change the name of this flood once again to the Cordilleran flood. Okay. So
why the Cordilleran flood?
Well, because the Cordilleran is the mountain range, that the Tetons, the Rocky Mountains, all of that is part of the Cordilleran. The Cordilleran concludes the Andes and the Rocky Mountains.
And that's okay, you're going to show us why. Yeah.
If you're really nice and say, please, I might. So in 1928, J. Harlan said this. The region, and he's talking about this region of Pacific Northwest, specifically Washington, eastern Washington. The region is unique. Let the observer take the wings of the morning to the uttermost parts of the earth. He will nowhere find its likeness. Now, we got to amend that because now we do know other places on the earth where we do find its likeness. Places that were not available to Bretz in 1928. There is a place near the Altai Mountains in where Mongolia and Siberia and China meet. There's an area right in there that has the same scale of flooding as we're about to look at. And the thing about that is we've got a giant flood on the other side of the planet that looks like it's the same scale. It has to be measured in hundreds of millions of cubic feet per second. Now, that is such an extraordinary event and such an extraordinary scale that it's problematic just to explain it once, as far as like explaining it up in Washington State. And if we recognize that over in the Altai Mountains, there's something similar on the similar scale, the next question is, okay, are they unrelated to each other? Or are they related to each other somehow? Well, and the first question you'd have to answer then is you'd have to look at the chronology. You'd have to look at the timing. And what is the timing showing at this point? Well, it's showing that what the dating we have is going to suggest that they're within a very narrow window of happening simultaneously. More dating is going to be necessary because there is some controversies about the dating of the Missoula floods. There's some controversies about dating some of the other floods that have occurred, like, well, the one we talked about in the last episode, the Bonneville flood. Mm-hmm. There's some controversies about the dating of that. We need a solid body of dating evidence that we amass through different formats. And once we do that, then we're going to be able to correlate how closely these events happened in time. And even if they were separated in time, could they have been part of or a result of a manifestation of some larger sequence of events that may be played out over several thousand years? Marjorie Burns, one of the researchers and authors that have spent many years studying this phenomenon in the Pacific Northwest, said that the geological detective tale that developed over the Spokane flood controversy is a tale of such sustained intrigue and epic proportions that its unfolding makes most fictional mystery plots seem trite in comparison. And then geologist Everett C. Olson, back in 1969, when the geological community was finally beginning to accept the reality of these floods, said that the sheer magnitude of the whole Scabland complex and the many ways in which it exceeds the bounds of normal stream erosion and deposition seem to justify, if indeed they do not demand, an outsized agent operating under extraordinary circumstances. Now, what in the world could be that outsized agent? See, this is, to me, the question that has not been answered. This was in 1969, right? And I don't think this question has been answered yet, although I think we're honing in on some answers, but there's a lot of reluctance on the part of the establishment view of this to be willing to go there. And it boils down to this. The establishment view, if I was to characterize it, is pretty much locked into thinking exclusively terrestrial, exclusively something within the terrasphere, within the planet, not something from outside. Whereas I think we have to be looking at the bigger picture and include cosmic phenomena as well. Mm-hmm. And when we do that, we might be able to actually identify that outsized agent. So, from my writing here, our goals through this presentation will be several. To convey a sense of the unfolding drama of discovery from the 19th century through the 20th and on into the 21st century of this greatest of all floods. To seek after the identity of the ultimate culprit in this drama, the outsize agent operating under extraordinary circumstances, which bears ultimate responsibility for the phenomenon in question, and to propose a radical theory as to the origin of these events of 13,000 years ago, events involving immense flooding whose reality we are only just beginning to comprehend. So, this is what I was calling my presentation, a decade and a half ago, Becket.
No way. How timely.
Way, yes.
The big picture.
Mm-hmm. The big picture.
So, Randall, now when you look at that picture, after looking and studying this for so long, you probably see something different than what most people see. They see the northwestern part of the United States. They see Canada. What do you see? What does that landscape tell you?
Well, I see a number of things that probably most people don't see. Let's take this area right here. We can see there's some snow caps there. If we follow the path of the Snake River, this is the Snake River right here. And this is where we left off with the last episode. We showed how down here you see the Bonneville salt flats. We followed the overflow of mighty Lake Bonneville right up here through Red Rock Pass, and then how it spilled out and carved out, over-deepened the pre-existing Snake River Valley, flowed up here, and then we came right up here to Lewiston and Clarkston, and we stopped at the Tammany Bar. And we found two different, we found two different sedimentary regimes. We saw a darker colored grayish, much coarser set of sediments that had very steep foresets, very prominent steep foresets, right? Then we saw on top of that, we saw a much finer grained, buff colored sedimentary layer. It wasn't quite as thick. It didn't have sweeping foresets. What it did have, though, was undulations that you could see very clearly. And I pointed out there was a transition in the type of layering, a type of strata, from quite level to where you then saw much more rippling. And I pointed out that this was the level was the incoming because it was at the almost at the distal point of its backflood. And you can see as it's moving closer and closer, it's slowing down, and then it stops, and then it begins to flow back out as the tributary valley drains. So what we saw there was the flat area where you had the very slow, sluggish. Then we saw the ripples where the current had reversed and was now flowing back out. And this is exposed in that Tammany Creek that gives its name to the gravel pit. Okay, so now if you go up into this area up here, this is called the Columbia Basalt Plateau. And it is basalt, which is an extruded lava rock. It forms under molten circumstances. It's igneous in origin, but unlike, say, the granites, it flows out and solidifies, crystallizes in the open air. Right, so its crystalline structure becomes very different because it cools fast. So because of the fast cooling, the crystals don't have time to grow really big, so you can see macro-scale crystals like you can often see in granites and andesites and things like that. But what you have is a finer-grained rock, and because of the way it cools, it can, in its composition, whether it's underwater, whether it's in the air, because if it flows out underground, some of it is going to be in lakes and rivers, right? And so it's going to form what's called pillow basalt, and then you have columnar basalt. You'll see some pictures of it here in a minute. And you have Hackley basalt. Those are the two most prevalent kinds, and they're very different. And we don't need to get into that, but it's mostly just the regime under which they crystallize, and also the composition of the distinct basalt flows, right, that you have these. And so that becomes one way that you can differentiate between basalt flows, and you will see pictures of that here. Okay, so this whole area here is a basalt plateau, and it's surrounded by mountains. Here's the Rocky Mountains over here, right? And here's the coastal mountains right here. And the Columbia River comes right down through here and goes through those mountains, and then it turns north and flows out to the ocean right here. That's the Columbia, right? So the Snake and the Columbia meet right there at that spot where that particular outcrop is. Okay, so now where did this basalt come from? Well, it came from this area right here. And that area right there is a lot of fault lines and fractures, which are called feeder dikes. And what that is that's the zone where the lava extruded from below, from down in the mantle, right? However, where it is now is not where it was when it began this bleed out, if you want to think of it that way. It started around 17 million years ago, and it was like a suppurating wound for about 10 million years. But as time went on, the amount of lava, basalt lava, flowing out, extruding from that wound, dissipated, and then finally the last gasp was pretty much about 6 million years ago, right? That's when the last layer of basaltic rock formed. However, this area was not where it is now when this started. In fact, you can trace its pathway back along the Snake River Plain right here, like this. Right up here, there's Yellowstone Lake right there, okay? That's where it was. So underneath, there's a deep-seated mantle plume rising up from deep down, from below the lithosphere. Rises up, and you can think of it rising up almost like a blowtorch or something, and the plate is moving over it. So as the plate is moving over, it takes roughly 10 million years from where it started out to where it is now. The plate is moving over it. Well, now this tremendous heat from below is coming up and basically melting the surface, and it's flowing out. So picture that you've got this area right here, and you back it up to here. And now you're at 17 million years ago, and over 10 million years, the plate moved in this big arc. And here it is right here, the area where all of this basalt extruded out and flooded this whole area of basalt. Okay, now fast forward to about 2.5 million years ago, at the beginning of the Pleistocene. That's when the glacial epoch really got underway. And you started having this alternating glacial and interglacial cycle. I believe we looked at some of that, didn't we?
A little bit, yeah.
Yeah, a little bit, yeah. So then for 2.5 million years, there was this oscillating cycle. Sometimes, and all of these mountains here were glaciated, right? Down solidly, you see where Lake Pend Oreille is right here. Mm-hmm. Pend Oreille was under an ice lobe that reached all the way down to Spokane, which is right about where my cursor is. So you can go here. It's about 50 miles from here up to here. And then all of this up here, I'll show you a graphic in a minute. Flathead Lake over here in western Montana was also the terminus. It was an ice lobe that ended right there. And we explained, I believe, that do you remember what moraine is?
I don't.
Moraine, no. Okay. Moraine, good for you. I like that when you're right there on top of things looking it up. Moraine is the material that's produced by the heavy glaciers shearing their way over the land, pulverizing and grinding everything up, right? So when we talk about moraine, there's different kinds of moraine. Terminal moraine occurs at the end of the snout of a glacier. Medial moraine is like a layer of this material, gravelly material. We usually call it till. It used to be called drift back in the old days, but till, if you have two valleys coming together and they're both glaciated, look at this. If the glaciers come together like my hands and then they're flowing down gradient, and they both got lateral moraine. So lateral moraine is along the sides. So if the glacier is grinding its way through a mountain valley, it's shearing off material from the walls. That becomes lateral moraine. So if you have two glaciers meeting together and there's lateral moraine, then they flow and become one glacier. So now you've got this big, thick, double thick layer of lateral moraine, but it's now within a coherent glacier because you had two separate tongues, came together, and then they sort of merged. So now down the middle of that bigger glacier, you've got this layer, thick layer of pulverized material. We call that, what did I just say? Lateral moraine.
Yeah.
Yes, moraine. It's medial moraine.
Oh, yeah.
Medial. That makes sense, doesn't it?
Yeah.
Then we also have recessional moraine. Now, you got a picture. This oversimplified way of thinking about it is that as the glacier's moving across the land, it's just like acting like a bulldozer, right? Which is part of the process. But more complex than that is the fact that the material, like even the lateral moraine, can be incorporated into the body of the glacier itself. The substrate material, the till below, can get worked up into the mass of the glacier. So if you were to take a cross section of the glacier, it wouldn't be nice, clean ice. It would be very dirty ice. And then there'd be layers in it where it's just almost like total, like gravel and boulders and sand and, right. So, and then the whole glacier is not necessarily moving all at the same rate. Now, when we're talking about glaciers, let's think about two glaciers in two states, living and dead. Living glacier has a zone of accumulation at the top of the glacier and a zone of ablation at the bottom, right? The material's accumulating up in the top, becoming incorporated into the glacier because you have layers of snowfall building up, layer after layer, year after year, and then eventually after about 80 to 100 years, the snow has piled up enough that there's pressure on the bottom layers, the layers that are 80 to 100 years old, and it converts it into a crystalline type of intermediary between ice and water. It's called firn, F-I-R-N. Then after another century or two, with more pressure building up, it actually becomes glacier ice, right? Now, it forms a layer. You can go in there and you can count those layers. And those layers just are like almost like tree rings. You can count annual layers, right? Because you'll have like heavy snowfall. You may even have a little bit of melting. So let's go back to this image here. Okay, so you can see that if you look carefully, you're going to see some darker traces over some lighter surrounding area. We're going to zoom in so you can see what that is. Now, what's interesting is if we look here, follow my cursor, this is the Columbia River coming here, and then it bends north, and it goes all the way up here into British Columbia. That's where its headwaters are. So you know that if the glacier came down all the way to this line right here, it totally covered Pend Oreille, it totally covered Flathead. So this is thick glacier. Once you get up in here, it's thousands of feet thick. And the only thing you're going to see is the very tops of the mountains peeking through, like it might be a mile and a half thick glaciers, filling all of those mountain valleys. You know, that you could go up there and, highways drive through them. Now, you hike, you can camp, there's lakes galore. They were filled with ice, thousands of feet thick. And not long ago. This is the late glacial maximum, right? So let's go here. This is sort of a artistic depiction of the late glacial maximum. Have you seen this before?
I've seen this picture, yes.
Yeah, it's a good one because it really kind of shows the you had the Laurentide, which was the big ice sheet over eastern North America. Then you had a totally separate ice sheet called the Cordilleran over here. Now, in this picture, this would be the late glacial maximum when the two ice sheets had coalesced. You also had a huge ice sheet called the Fennoscandian that was over northwestern Europe. Okay, now with all of this ice here, sea levels are 400 feet lower. Because where did this ice come from? Well, it's frozen water, isn't it? And where did that water come from? Well, it came out of the oceans. So one of the unanswered questions about this whole ice age business is how exactly does nature go about starting an ice age, a glacial age from an interglacial age? How do you do that? So by what process? I mean, now in our current climatic regime, we have snow falling over, say, Canada and the northern United States. Where I grew up, sometimes that snow could get many feet thick, right? But then comes spring, usually, what happens? It all melts. It goes back into the hydrosphere. We call this the cryosphere. It's the regime of global ice, the world of ice. The hydrosphere is water, and that could include everything from the oceans to rivers to lakes, creeks, and subterranean water, which we know there's a lot of, right? So that's the hydrosphere. So what happens then is every spring in the northern hemisphere, all that snow turns back to water and flows ultimately into the groundwater or back into the oceans, right? It doesn't stay perennially each year, adding another layer. It melts away, right? But in order to have an ice age, you have to have 1 year where spring doesn't come. Then the next year, spring doesn't come then either. And then the next year, spring doesn't come. And now here's the thing. What it's looking like is when we're trying to sort out what happened here is like, okay, so in the older models, we're thinking 100,000 years or more. You've got this great ice age. Slowly the ice grows and the mass accumulates and the ocean levels go down. Then for 100,000 years, you've got this big, intact, more or less stable ice sheet. And then 50,000 years that it slowly melts away and ocean levels come up. The whole process takes a minimum of 100,000, maybe 150,000 years to complete the sequence. Mm-hmm. Well, now that we have dates, all kinds of dating in hand, we know it ain't that simple. In fact, there could be several interglacials or interstadials. I don't know if you remember, I think we introduced those terms in the last episode. And if I go, here's the big oscillation, full glacial maximum like it was 15, 20,000 years ago, interglacial like it is right now, right?
Right.
Okay, so you have oscillations that might go like this, but then you also have oscillations that might go a little less. So you have a stade or a stadial, which is where it gets colder and the glaciers grow, but they don't get as big as what you're seeing here. Then you might have an interstadial where the glaciers melt away largely, but there's still significant glacier mass left, right? So sea levels then obviously would still be lower than now. So we're using two types. We've got present, that's an interglacial. Late glacial maximum or any glacial maximum would be like 15 to 20,000 years ago, right? So you've got oscillations now that are between those two is extreme, but you've also got oscillations that are less than that. So that's why the reason for two additional terms. So you have glacial maximum, you have glacial maximum, interstadial, stadial. Then you have interglacial and interstadial. So interstadial is still going to be colder than now, and there's still going to be some ice, but not as much as you're seeing right here, okay? So it helps. If you can learn these terms, it really does help talking about this. So now what we're going to do is we're going to come around just looking on it from the northern hemisphere, the western hemisphere. And in this graphic, you can see pretty clearly the two distinct ice sheets. So you have the Laurentide ice sheet and you have the Cordilleran ice sheet. And again, all of this is the Cordilleran mountains. It's all part of that whole system, right? And then you can see that there's this line here. And in this graphic, they're pretty much have met each other. Now, between 13 and 15,000 years ago, roughly, there was a warming from the late glacial maximum. in that warming, both the Cordilleran and the Laurentide shrank back to maybe 80 to 90% of their maximum extent. When they did that, this zone between the two ice sheets opened up. If you hear the term the ice-free corridor, that's what it's referring to. It's referring to this zone between the Cordilleran and the Laurentide ice sheets. Now, the Laurentide was centered. There's a major dome pretty much right over Hudson Bay. That was like the thickest part. Some estimates put it up to 2 miles thick right there. I don't know if that's true, but I think we could say that it was at least 1.5 miles thick. So if you're somewhere, in an urban area where you have, like here, in Atlanta, you can go down the Bank of America building, I think is 1,200 and some feet high, right? It's the tallest building in Atlanta. So if you go there and you get a good view of I used to take students, there's an overlook where you can kind of see a great skyline view of Atlanta from maybe 5 miles distant or so. You can see the tallest building there, Bank of America building, 1,200 and some feet high, or maybe it's 1,100 and some. Let's see, 1,200, No, about 1,100. Bank of America building, Atlanta. How tall is it? I'm going to say 1,100 and some feet.
It is 1,023 feet.
Oh, even smaller than, okay, so 1,023 feet. But it's the tallest building in Atlanta. So if you stand there basically and try to imagine 5 of them on top of each other, that's like, conservatively how thick the ice was, right?
Wow.
That's pretty extraordinary when you start thinking about it. Now, here's the problem. It appears that you get back around 30 to 40,000 years ago, and right up in this area, right up in here, the area of the Laurentide ice sheet, forests were growing. Forests were growing. Let that sink in. If there were forests growing, then there was not a big unbroken ice sheet, was there?
No.
Couldn't have been. And that's well dated. So this, what it did was, it was assumed that the explanation for glacial and interglacial ages was explained. And that was based upon the Milankovitch forcing, which is the 3 different ways that the Earth-solar geometry shifts. Shape of the orbit, the tilt of the axis, the distance, whether it's aphelion or perihelion. Those 3 together will affect sometimes where there's more heat reaching the northern hemisphere, sometimes more heat reaching the southern hemisphere. And sometimes it'll be neutral. The forces will cancel each other out. Other times they can mutually amplify each other. So by carefully working out those cycles, it was assumed that there was enough explanation for how you could go from a glacial to an interglacial if you're talking 50 or 100,000 years. Mm-hmm. However, you're talking 20,000 years, or rather say 30,000 to 40,000 years ago. Well, now you got problems. And the problems are the rates of glaciation and the rates of deglaciation. That's a problem that hasn't been resolved as we sit here talking right now. And because, why? Well, let's talk about deglaciation. To convert ice into water, you have to have heat, right? Now, we could look at some early studies that were done in the 70s about the energy requirements to get rid of about 6 to 7 million cubic miles of ice. Now, imagine this. Again, I like to take people out where you can kind of see things and see skylines. Imagine an ice cube that's 1 cubic mile. And you're standing, again, go back to thinking, Bank of America building, tallest building in Atlanta. Mm-hmm. And you're looking at that building, and you stack, 5 of them on top of each other. That's the thickness of this ice cube, and it's the same distance like this and this. So you got this huge ice cube. All of a sudden, instantaneously, it melts. Well, and obviously in the surrounding terrain, you're going to have some hellacious flooding, aren't you? Well, now imagine you've got that ice cube times 6 million. See what we're talking about here?
Yeah.
We're getting into things here, territory that I have found, having studied this stuff now for over 4 decades, really going on 5 decades, I realize that very few people out of the human species have any inkling of any of this that I'm talking about right now. Have thought about it zero. I mean, now there are small members of the scientific community, absolutely, and I could probably list them, and I'm going to guess worldwide, maybe a few hundred people out of 8 billion.
Alive today, or who have
Alive today, yes.
asked this question? Okay.
And
how many people do you think have taken this question seriously over the last, let's say, 100 years?
Well, if we go back 100 years ago, we're in 1925, and at that point, the answer would be 1.
Bretz,
yeah, 1. That was it, 1. 1 person. Then we jumped ahead to a quote from a geologist from 1969. And by 1969, the geological community was beginning to accept the reality of Bretz's megafloods. But even then in 1969, how many people do you think really knew about it? A few dozen maximum. How many do you think had actually gone out and spent hours, hundreds, maybe even thousands of hours in the field investigating?
10. Maybe
10, yeah, 15, maybe 2 dozen. I'd like to find out. There was an expedition out, I think it was in the 60s or 50s. There was a major turning point when the geological community finally accepted the reality of these floods. But I think that what they did was they tried to force it into a model of uniformitarianism. And that's where it's still at. If you look at this graphic that you see right here, notice the box with the black boundary. You see that?
Yeah.
Yeah. Okay, to me, remember I said there was a graphic that I think kind of represented the psychology of the thinking around this? And this is it right here. The modern, the mainstream theory will not go outside this box. That's it. I mean, the origin of the flood is within this box. The entire terrain submerged by these floods was within this box. And I'm arguing that no, it's much greater than that.
So why won't they go outside the box?
Well, because, okay, so you asked a good question. Because the origin of the flood is a quote-unquote ice-dammed lake. An ice-dammed lake. So while you're there, look up ice-dammed lake.
And my guess is that's the only place that they could find origin of an ice-dammed lake.
Well, remember, here's what the uniformitarian creed likes. It likes to find a modern analog for any ancient process that we happen to be looking at, studying, trying to understand. And it's a very powerful and very useful technique of understanding past events that have left evidence, but the events themselves are no longer operational. So we're only looking at the aftermath of those events, right? What did you come up? Did you find anything?
Yeah, I did. You'll have to unshare for me
Let
to share.
me unshare here. Yep. Stop sharing. Okay. Yes, there we go. Oh, boy, they got a lot of good, cool graphics there. Let's see. Ice-dammed lakes at melting glaciers is decreasing. Flood hazard, Now, that one, the bigger thumbnail there where it says flood hazard of ice-dammed lakes at melting is decreasing. Well, why is that? It's decreasing. So the flood hazard of ice-dammed lakes is decreasing. Well, it's because the glaciers are shrinking. Now, remember, this is something that, again, I've been saying for years, but probably most people who are listening don't understand this or haven't really thought about it, and this is a fact. If we go back, we're looking at the late glacial maximum on the two graphics I was just showing, right? So you got this maximum of extent of ice, and after that ice was completely melted away, which interestingly coincides pretty darn close with the actual beginning of recorded history, around 6,000 years ago. Okay, when that ice was completely melted away, sea levels were actually higher than now for a while, 4, 5, 6 feet higher even than now. And then sea levels went down again. Now, if we fast forward throughout the entire Holocene, which is the modern epoch that is now dated to have begun at 11,600 years ago, plus or minus a century, but that's close enough, 11,600 years ago. Within that span of time, immediately after the glaciers were almost gone, the climate of Earth went into what was called originally the climatic optimum. And it was during the climatic optimum that sea levels were higher than now. Why? Because there was less ice on the Earth, glacial ice amassed on the surface of the Earth than there is now. Okay, so now fast forward to about 800 years ago, and there was a major shift in the global climate. We went from a period called the medieval warm period, which we've talked about, the period, the great Gothic cathedral building era, that only could occur when you had a rich and prosperous society with a considerable amount of leisure time. Because without leisure, if you're grunting around, foraging, trying to hunt and gather, you're not going to have a lot of time to sit there and figure out advanced mathematics. You're not going to have a motive to get intimately aware of the movements of the heavens, the cycles of the moon and so forth. You're not going to have a need for that. But when you have an advanced society where you have a division of labor and you have sufficient leisure time, well, now that's when you can begin to see the cultivation of the arts and the sciences. This is exactly what we saw during the High Middle Ages, is that global warmth was a very beneficial thing. And there's evidence that the medieval warm period, which we could say lasted roughly from 1000 AD to 1300 AD, 300 years. Now,
what was the temperature then compared to now?
It was 1 to 2 degrees warmer than now. We could get into some of that, talking about specifically how do we know that. Well, that the warmer it gets, the higher altitudes trees can grow. Mm-hmm. So we can go back and we can find tree lines from the medieval warm period that were like 1,000 feet higher than now. And we can conclude from that, well, how warm did it have to be at that elevation, rather not altitude, elevation, in order for those particular species of trees to be growing there? That's just one way. Also, we can look at lakes, because if the climate warms up, lakes will warm up. Cooling down, lakes will cool down. And that will affect the variety and type of species of creatures that live in the lakes. Same way with the oceans. There's multiple ways we can look at tree rings, right? Tree rings are a reflection of temperature and moisture regimes. Like if you have a drought, it can be hot, but you'll have very, very narrow rings, very poor growth. On the other hand, if you have warmth plus rainfall, now you're going to get nice, big, fat, juicy tree rings, right? There are all kinds of ways. These are proxies, what we call proxies, by which we can reconstruct ancient environments. Okay, so medieval warm period came to an end in the late 1200s, early 1300s. the planet got colder, ice began to accumulate, and glaciers grew. So between roughly 1300 and 1850, you had the multi-phase Little Ice Age. There were more or less like two major phases with sort of a break in between. At the end of phase 2, glaciers worldwide were more extensive than they had been since the end of the Great Ice Age. For most of the Holocene, most of those 10,000 years at the end of the Great Ice Age, down until about 800 years ago, glaciers were smaller, more retracted. With the onset of the Little Ice Age, glaciers grew considerably, right? Now, with the global warming that began about the mid-19th century, we could use a round number of, say, about 1850. With the advent of that warming, the Little Ice Age glaciers, which had swollen to the biggest they'd been in 10,000 years, basically, began to shrink back. Well, as they're shrinking back, what does that imply? It implies they're melting. So obviously, if they're melting, there's going to be meltwater, right?
Right.
So as they're melting back, it's producing volumes of meltwater, and oftentimes those volumes of meltwater can become entrapped. And if you go back to those graphics, let's go back to those graphics that you were looking at there. And we'll pick one out. Okay, let's see a crossing. How about that one right there? Let's take a look. Yeah, zoom in on that. In fact, you could probably, yeah, there we go. Good. Look at here. All right. So we've got glacier evolution. So let's start down here where it says moraine dammed lake. Pro-glacial. That means in front of the glacier. Now, remember we were talking about moraine, right? And we're talking about the glacier pushing this stuff down.
Yeah.
Well, what happens then? It creates mounds of this moraine, right? And that moraine can be hundreds of feet thick. Be 300, 400, 500 feet thick, right? Now, what happens when the glacier melts back? Well, coming off the front of the glacier, you have the meltwater, right? So the moraine there, the terminal moraine can act as a natural dam that will cause a ponding of meltwater. Now, as the more the glacier shrinks, the greater that proglacial lake will become, right? At some point, it might breach the moraine dam. Now you have an outburst flood. Because remember, the moraine is not like hard rock. It's just piles of rubble. It's stuff that the water pressure can percolate through and drain. Now, there is a lake called Lake Chelan up on the Columbia River. Beautiful lake. And it is still dammed in by the terminal moraine of the glacier that filled that valley at the end of the last ice age. But so you've got, look at here now, you've got the white, which is the glacier. So take your cursor and go from the moraine lake up where it says ice dammed lake. Okay, so now picture that. You've got, what's happening there is that you probably would have had that valley that is now occupied by the ice dammed lake was glacier. And it melted away. Maybe it's the south facing mountain slope, so it gets more heat from the sun. It melts faster because, for one thing, it's smaller. It's not as massive as the trunk glacier, the main valley glacier, right? So what happens is as that valley glacier melts away, it forms a lake that is now held in by the glacier. So here you can see there's two types of lakes now that form. We've got a moraine dammed lake held in by the glacial moraine, and now we have an ice dammed lake that is actually held in by the ice itself. So this is something we have witnessed dozens and dozens of times, lakes forming behind both moraines and ice dams. Now, the model that was used to try to explain the existence of the Missoula floods was a larger version of what you're seeing right here, an ice dammed lake. Okay,
Have to be a big ice-dammed lake.
It had to be, well, you can actually calculate the volume of that lake, and because we know the high elevation of the lake was 4,200 feet above sea level. Maybe a little more. It may have been at 4,250. But there was a relatively stable, just remember what we learned about Lake Bonneville. It created shorelines, didn't it? We call those shorelines strand lines in geological lingo, the strand lines. So you can see strand lines, and I'm going to show you some pictures of strand lines in a minute. And we can look at the top strand line, and we can follow that strand line. I mean, it's broken in many places, but we can find it again. And it's right at 4,200 feet above sea level. Okay, so if we were to go to Missoula, Montana, Missoula, Montana is about 3,200 feet above sea level. So at that point, we can now estimate that the depth of the water there was right at about 1,000 feet deep. Right? So good. We've got this supraglacial lake. Okay, supraglacial means that it's just formed on top of the ice. That's all that means. Also notice at the very top up there it says ice flow. Recall that I said two types of glaciers, living glaciers and dead. This would be living.
Yeah.
The ice is flowing. It's moving. There's a zone of accumulation. It would be up there on the top end, and then a zone of ablation, and that would be the snout where it's melting. Is all this making sense so far?
Yeah, yes.
Good,
yeah.
Good. That's great. And then you can see here, go to that lake where it says lake evolution, horizontal and vertical, and you see some red arrows showing that typically it's not unusual for lakes to drain through the ice and get to the bottom of the ice sheet, right? And that's what you see indicated right there.
Yeah.
Let's see what else. Back out from this and let's see what else you got here. Yeah, let's look at that one. Okay, so we've got, what is that? Something glacier. Yeah, so there, some good graphics. Where a glacier blocks a trunk or tributary valley, and where a glacier fills an overdeepened valley created by glacier erosion. So you've got the graphic on the right. You can see ice flow. So, and then it's calving off, which is breaking off and forming icebergs. Let's see, what do you got there on the other one? You've got superglacial lake, you've got ice flow, so these are all living glaciers. Here was the question. All of this is context for understanding the question. I haven't forgotten the question. The question is what is the model for the formation of the channel scablands in the Missoula flood? Well, it's what we're seeing right here, basically, that you had an ice dam, and that ice dam filled the valley that is now occupied by Lake Pend d'Oreille. And might as well go back to our graphic here. So we've got where all the light blue is, that is channel scabland for the most part. Now, Willamette Valley down here is not channel scabland because this was a back flood. In other words,
I
up
can't
here where
see
the
your cursor anymore.
Oh, sorry.
Oh, there it is.
I was on the wrong screen with it. Okay, so here is the area of the channel scablands, which is in the area of the basalt plateau, right? Then this is the Columbia Gorge, comes down through here, and then right here at Portland, it diverges to the north and then diverges to the west, and it drains out right here at Astoria. Portland itself is on a huge delta bar that was built by the floodwaters when they made this this northward turn right here. But then the water, right here is this area called Colima Narrows, and the water got constricted in Colima Narrows which is actually quite large, and there was so much water coming down through the Columbia here that it backflooded all the way to the south of Willamette Valley. And where Portland now is was at least 400 feet underwater. At least 400 feet. Now, the dark blue is Glacial Lake Missoula. And Glacial Lake Missoula, if at full pool, 4,200 feet above sea level, would have been about 600 plus cubic miles of water. That's a lot of water, right? And the idea is that it's held in by an ice dam right here. And at some point, the ice dam gave way, and all of this water drained out through the Spokane Valley and then spilled out over the Columbia Basalt Plateau, cutting this branching channels of erosion through the topsoil, exposing the darker basalt below. Then it all came together right here at Wallula Gap. And at that point, all of these multiple channels of flowing water converged through that gap and then flowed down the Columbia and out to the ocean. Now, that is just a much, much larger version of something that we could sort of seen kind of mimicked today. The question is, though, is that feasible? Okay, so clearly at the lake ice dam interface, that's where the water's going to be the deepest, right? Wouldn't that make sense? And as you're moving away in the distal regions of the reservoir, the water's going to be getting shallower. All right, so this graphic kind of shows the whole terrain. You can see the Columbia Basalt Plateau here. Over here is Flathead, and Flathead Lake was one of the ice lobes. Here you see Pend Oreille. Here you see the Okanagan River coming down. And you can see what's called Grand Coulee right here. I'm going to introduce you to Grand Coulee in a minute. Okay, we're going to speed through some of this. Okay, so this satellite photograph, well, let me see, this may be Google Earth, or I may have actually captured this before Google Earth. But here, in this, here's the basalt plateau. And you see this buff-colored light here. That is topsoil called loess, L-O-E-S-S, loess. And it's a very fertile soil. But the thing is that this whole area is semi-desert. It's called semi-arid. It's a semi-arid. The Cascade Mountains here form a rain shadow. So the moist air coming from the Pacific, once it hits the Cascade Mountains, it has to start moving up. But as it moves up, it's cooling. As it's cooling, it loses its competency to hold moisture, and it releases that moisture. So you get huge amounts of rainfall on the west slopes of the Cascade, and only small amounts. I know that over the Columbia Basalt Plateau, I think the average rainfall is about 15 inches per year. It's probably 5 or 6 times that much on the western side. That's why you have rainforests there, right? So it's in the rain shadow. So it's semi-arid. But the basalt rock is covered with all of this highly fertile topsoil called loess. Well, so it dawned on people, like even going back to the Franklin Roosevelt administration, that if you could irrigate this area, you could get some pretty impressive agricultural activity there. And that's what they did. So in the 1930s, they built Grand Coulee Dam, which is right up here where my cursor is. At the time, the largest reinforced concrete structure in North America. It was quite a heroic undertaking. And then here was Grand Coulee, Upper and Lower Grand Coulee, that gave its name to the dam. We'll be coming back to talking about Grand Coulee in a minute. But notice here, what you're seeing in these darkened areas, these branching areas like this, is the exposed basalt that's under the 100 to 200 foot thick layer of topsoil that's laying right on top of the rock, right on top of the basalt, right? 100 feet, 200 feet thick. When the floods swept down from the north, they quickly washed right through the 100 feet or 200 feet of lost topsoil, hit the bedrock, and then actually began scouring and incising, cutting into the bedrock itself. That's what Grand Coulee is. And there are many lakes throughout these areas called scablands, but you can see very clearly the scars. That's what these are. These are giant scars in the landscape. And you can see these scars emanating from what would have been the glacier front, right? So the glacier, in fact, look at my cursor right here. Do you see this kind of arc-like arcuate form? That's terminal moraine. And you can see the difference. When you get south of the terminal moraine, it's agricultural. But the terminal moraine itself is so bouldery and gravelly that there's really no way to grow crops on it. So you can see this very distinct line of demarcation. So follow my cursor, and this would have been the edge of the ice front right here, like this. Right across here, and then there was the Spokane Lobe. Here's Lake Pend Oreille. The Spokane Lobe reached down right here and terminated right at about Spokane, right in here. And then you come across, and here's the Okanagan Lobe. Now, coming off of the Okanagan Lobe, you can see there's a channel right here. That's called Moses Coulee. This we call Telford, the Telford Scabland Tract, after the town of Telford, that's right up here in the north sector. And this we call the Cheney Palouse, after the town of Cheney, that's right up here. And I don't know the origin of the term Palouse, but this is all of this loess is referred to, is called the Palouse loess. Maybe it's after the Palouse River. This is the, well, you can't see it on here, but the Palouse River comes in from up here. Let's go to the next one. Okay, we've seen that. And this is a more detailed map of the lake. And this boundary line here is at the 4,200-foot elevation. And you can see here, it's a very complicated lakeshore. It's not like a nice big round lake or anything. It's extremely intricate. And you can see here the Clark Fork River. You can see that water in the Bitterroot Valley, notice up here, ice dam, right? So you got this ice dam that forms here. This ice is coming down out of Canada, and it blocks off the flow, the northwest flow of the Clark Fork River, right? So the ice comes, blocks off the flow of the Clark River, and then it begins backing up. And it continues to back up, and the lake level rises against the ice dam. And as the lake level rises, it's back flooding into all of these valleys. And ultimately, finally, it reaches the most distal point, like at the southern part of the Bitterroot Valley. Like if you could go back, 12 to 15,000 years ago, whenever this lake was at maximum pool, you could stand right here at the edge of it. You'd be on the shoreline of this lake that's like basically the volume of one of the Great Lakes, right? Wow. Just like go imagine you're standing on the shoreline of Lake Superior. Same thing over here. When you see this right here, you can see how the water backed up. Well, then the theory is that the ice dam, which you can see right here is at the Idaho-Montana border, it gave way, and all this water drained out. And that water draining out spilled out over the Columbia Basalt Plateau, because this is not on the Basalt Plateau. This is in the mountains. This is the Bitterroot Mountains here. And that water drained out, the pool emptied, and then after 50 or 100 years, the ice came back and the lake filled again, and then repeated that dumping. And then it happened again, and then it happened again, and then it happened again, and again, and again, and again, and again. And some of the theories are that it happened 39 or 40 times. There's one geologist that even thinks it happened 90 times or more. And I think, personally, that makes no sense at all. It just doesn't make any sense. But the belief is that you don't have to go beyond. This is the theory. We don't need to go beyond this. The ice comes back, dams the Clark Fork Valley, the lake fills up, bursts through the ice dam, and drains out, and then fills up again, and it does this repeatedly. Well, that's the modern model because we see these, they're called self-dumping lakes. So you get spring melting, a lake forms, it pushes its way through the ice, and it bursts out. Then the next year, or maybe 5 years, 10 years later, you get another full pool of a lake, and it bursts through, an outburst flood. In Iceland, you have volcanoes that are under the big ice masses there. So if a volcano goes off, it melts a bunch of ice and creates a reservoir. Then that reservoir of water will force its way through the ice and discharge at the snout of the glacier. The Icelandic term is Jökulhlaups. The Jökulhlaups is the outburst flood. So that is what's been taken as the model to explain what we're looking at right here. It's just a larger version of modern ice-dammed floods that we've witnessed. Okay, fair enough. That's a good starting point. But I think once you get into it, the more you look at it, the less sense it makes. Now, I hope what I've just explained, you can understand why it's confined within that box. That box, because you don't have to go outside. With this model here, there's no need to go outside that box.
It just happens many times.
Yeah, and of course, to me, what is not being addressed here is, okay, what is the ultimate source of the water? Now, where's the water coming from? Is it rainfall? Is it snowmelt? Some combination thereof? And it has to be warm enough that that this water is not freezing into permanent glacier ice. So it has to be warm. So there's an implication here about the state of the climate when this is happening. One of those implications have to do with the glacier mass itself that's forming this ice dam. And that's this. When you look at the continuum of glacier types, the most stable type you've got is called a polar glacier. It's so cold, there's just very little meltwater. The bottom of the glacier is frozen to the ground beneath. But if you get into warmer climates, then you have a tempered glacier. Tempered glaciers are the ones that can move fast, they surge, they can form meltwater. In fact, they almost always have a layer of meltwater between the bottom of the glacier and the ground. That's important, which causes tempered glaciers to be much more dynamic, because they can glide on this water layer, right? Mm-hmm. But then what happens is if you've got water rising behind a glacier, the higher it rises, the more pressure it's going to be at the bottom of that water column, isn't it? Well, how deep was the water right up here? Well, I've been through this valley many times. We can look at topographic maps. We can use an altimeter, both of which I've done. The floor of this valley is right at about 2,100 feet above sea level. And
you were saying that
the high water mark is at, so this line forming the shoreline all the way around here is at about 4,200 feet above sea level. So the floor of the valley here is about 2,200 feet above sea level. So from there, you can quickly calculate, you can see instantly, well, the depth of the water here was about 2,000 feet. Now, go back to we were talking earlier about, Bank of America building was 1,000 and what was it, 23 feet?
Yeah, 1,000.
1,032. So if the water got to be up to that, remember I said it might have gotten up as high as 4,250, right? So then the Bank of America building, if you took two of them and stacked them on top of each other, it would just reach the top of the water here. Now, let's think about this. When you have a water column that's 2,000 feet deep, what kind of pressure? You ever been scuba diving?
Once.
How deep down did you go?
60 feet.
Yeah, that's pretty typical. Why didn't you go deeper?
Because it gets very, very difficult to, and there's a lot of
pressure.
pressure.
A lot of pressure. Now imagine going down 2,000 feet. What kind of pressure are you talking about? Well, you're talking somewhere in the range of 950 to 960 pounds per square inch at the bottom of that water column. Let's say 950 pounds per square inch. Well, then we go that times 144. That means you've got something like 70 tons of pressure every square foot. Wow. Now, is that even feasible? Is that possible? That you could have, let's think about what's the highest dam in North America? Hoover Dam, right? Look up Hoover Dam and tell me how tall it is and how deep the water pool is behind it.
720 feet tall.
720 feet. So in other words, Lake Missoula there at the ice dam was 3 times deeper than the height of Hoover Dam.
Yeah, and it says the maximum water depth is 590 feet.
590 feet. Okay, so I'm going to go 2,100 feet. Divide by 590 means that, 3.6 times deeper than the pool of water against Hoover Dam. Now, Hoover Dam is a engineered structure, steel, massive amounts of steel reinforcing, bedrock grouting. You know what bedrock grouting is? Look up bedrock grouting. Now, this is something that had to be done when they built any kind of a dam. In fact, this was one of the things that caused the failure of the Teton Dam was improper bedrock grouting. What does it say?
It says rock grouting is performed to fill apertures with a predefined radius of ejection grout hole.
So what they're
rock
doing
grouting?
is they're injecting concrete-like material under high pressure into all of the cracks and apertures and voids that are in the bedrock surrounding a dam.
I see, yeah.
And why do they do that?
So it's
because-
less permeable, so it's less damageable.
So it's less permeable, absolutely. Now, if you look up the Great Teton Dam disaster, what you found there was insufficient bedrock grouting, led to the last big monumental dam catastrophe failure built by the U.S. Army Corps of Engineers that failed back in 1976.
The dam was made of wind-blown silt.
Not a good material.
Yeah. It says the grout curtain that was supposed to prevent the silt from washing away had gaps in it.
The grout had gaps in it, yes.
Yep.
So now, I think we're getting a picture here of this. Here's the problem. Maximum depth of water against a dam we see in North America. What was it, 500 and what?
520 feet.
520 feet. So we're looking here at a depth of water almost 4 times greater. And the dam that's holding that water in under that tremendous pressure is ice, glacial ice. Now, if you consider glacial ice, particularly moving tempered glacier ice, we saw on the graphic a supraglacial lake, right? So let's say you got a glacier, it's in a temperate environment. All winter it's been accumulating some snow and stuff on top. Now spring comes and you have melting on top of the glacier. And that melting forms supraglacial lakes. Well, typically now, a lot of glaciologists have studied those glacier lakes and found out that they're only ephemeral, right? What happens is they reach a certain size and suddenly they're gone. They disappear. Where'd they go? Well, they just went right down into the ice. Now, they've done dye experiments where they'll put a dye in the water. Then typically the lake will disappear. Then there'll be a discharge at the snout of the glacier that they'll know came from that superglacial lake because it's got the dye in it, right? And typically, bear in mind, that is moving under pressures, a superglacial lake. Well, you're going to have 14.7 psi atmospheric pressure, and then you're going to have whatever pressure of the body of water itself, which is not going to be hundreds of feet thick. It's going to be maybe a few dozen max, right? But that's enough to cause that ice to percolate, that water to percolate through the glacier, get to the bottom of the glacier, and flow out and discharge from the snout. Now, see, the more you start thinking about this, the less sense it makes. How is it that even in one circumstance you could have water backing up 2,000 feet deep against ice? What happens when we look at modern examples of ice-dammed lakes in terms of peak discharges, in terms of maximum lake volume, and so on? What do we find? Well, we can open some other slides in a minute, and we can see by comparison what we do find. But let's go on here. Very interesting stuff, but no time to explain what that is now, other than note flow velocity. Very important. Because, again, remember we've talked about this. The amount of erosion is dependent on flow velocity. The faster the flow, the more potential there is for erosion. When you decrease flow velocity, you now can shift from erosion to deposition. So those were the two extremes, erosion and deposition. The faster the water is flowing, the greater the erosion. The slower, the greater the deposition. And then typically along one, let's say, river flow or one channel with a more or less uniform flow in it, you're going to have a threshold where it shifts from erosion to deposition. And that happens in a number of different places. One, if you go from a narrow valley to a wide basin. Fast flow through the narrow valley, slower flow into the basin. So erosion in this constricted area, deposition in the expanded area. Also, gradient. If you've got this, it's flowing fast on the steep slope. You get to a shallower slope, the water slows down. Again, erosion, deposition. Mm-hmm. Makes sense, doesn't it?
Yes.
So when you understand these things, when you're out in the field, you can begin to actually read the landscape, which is ultimately what this is about and why we're doing this, is I'm trying to get people interested in reading the landscape, because that is when this story will begin to reveal itself. Now, you can read all the papers in the world, which is great. You can look at photographs. You can look at drone footage. You can look at videos. You can look at satellite. All that helps. Ultimately, though, you have to get out in the field firsthand to get a sense of the magnitude of this phenomena we're talking about here. Let's go on. Okay, this is an interesting digital elevation model where color relates to elevation. So you can see very clearly the basalt plateau, right? In fact, it goes down. This is all part of the basalt plateau here, Columbia Basalt Plateau and Channeled Scabland. And then up here is Lake Pend Oreille. And this is very crude, but it gives you the idea. This is the Clark Fork River Valley, and the ice dam would have been right here where my cursor is. The theory is that the ice came down all the way to Spokane, which is right in here, terminated here, and then the lake, all 600 plus cubic miles of it, backed up into the mountain valleys of western Montana. Finally, the glacier mass couldn't hold it back anymore. It gave way, and all this water drained out and spilled out across. And ultimately, all of the features from Moses Coulee to Grand Coulee to the Telford Scabland to the Cheney-Palouse Scabland all originated over here. Okay, that's one of the implications of the dominant theory, right? And then a couple of things to call your attention to. Right here is that gap. It's called Wallula Gap, right? I call that the gathering of the waters, the point where all these waters flows came together flowed through this gap and down through the Cascades here, the Columbia Gorge, which is a magnificent route right through here to travel. And we did that last September. We did the Columbia Gorge tour. So we started up in here, we explored this area, and then we came down through the gorge, and we ended up at Bridge of the Gods. It was quite an impressive tour.
Where are you going in May? Where will you be exploring in May?
Well, the plan there is the Bonneville flood. Start in Utah, travel up and follow the Snake River, up to Hell's Canyon. So anyways, you're starting to get the picture here, I think. And I've tried to intimate some of the things that I think I'm kind of pointing in the direction where I think the standard model breaks down and why we have to look beyond. The other thing I wanted to point out was these ridges that you see through here. Those are called anticlines. Now, whenever you have pressure, let me grab a piece of paper here. So let's say you have lateral pressure on the crust of the earth. So, in other words, compressive, like this. You can get a fold. The fold can go up, or the fold can go down. This is a syncline. This is an anticline. And this is a monocline. And we've got all three of them here in this terrain. We have some synclines. Those are those ridges, those east to west ridges you see on the graphic. And that's from compressional forces causing this upwarping. Other places you'll have synclines. Synclines are sometimes hard to identify because they'll get filled with sediment and they're not visible from the surface, right? But if you can dig through or have ground penetrating radar, oftentimes synclines can be identified because you can find rock that's at the top of the downwarp. And that downwarp might be miles wide, right? But on one side, you've got layers of rock, and you can find on the other side matching layers of rock. And then you take some core samples, and you discover the same layers of rock, but they're down several thousand feet or whatever under sediment. So now you can see that this is a synclinal downwarp. This is an anticlinal upwarp. And then if you have a single where it goes from one level up to another level, that is a monocline. And I'm going to show, like, think of the word cline, like incline, right?
Yep.
Yeah, and I'm going to show you a monocline here in a second. So those are important because that water flowing south hit those ridges. So it created some very interesting geomorphic work. Like this one right here is the name of it. It'll come to me in a second. Let's see. This is Frenchman anticline, and this is its name. I'm blanking on its name, but right here particularly, you can see on the sides, on the northern flanks, the massive amount of upwash that was washed against it by these enormous currents coming from the north. And you can see here there are these basins. This is the Yakima Basin. This is Pasco Basin. So when all this water came down, there was so much water coming down. There was more water coming down from multiple sources than could discharge through Wallula Gap. So what happens? The water pools up and backs all the way like up here into Yakima, all the way here, and it was about 1,000 feet deep right at Wallula Gap. I took Graham Hancock. We went up on this overlook, and we stood up here, and we could look out over Pasco Basin and really get a sense, because we were right at the high water mark. So we're standing up on the edge of this huge cliff overlooking Wallula Gap, and I brought Graham there. I said, Graham, we are standing right now at the high water. So if we were here during the flood, we would probably get washed right off of this knoll. If we walked over here, to the northwest to slightly higher ground, we could have stood there and watched the water spilling over the tops of Wallula Gap. And here's another closer up where you can see, here's the anticlines and the basalt plateau right in here. You can see it's very distinctly outlined. And the old route of the Columbia River that came down this valley here before the basalt floods came right down this way here. But when the basalt floods came, they dammed it. Now, this is happening 16, 17 million years ago and caused the Columbia to flow around the western rim of the basalt. Now, right here on the east side of the Columbia, it's basalt. On the west side, it's granite. It's very distinct, and you can see there's several places where you can see the two types of rock just adjacent to each other, right? Now, when the ice sheets came out of the north, the ice sheet, now this was the original route of the Columbia, it was this way. But when the ice came out of the north, it blocked this northward arc here, so it forced the Columbia to flow right over the top of the basalt. And it cut down a new channel. So the old channel was completely abandoned because of the ice. The ice cut it off, causing it to divert. The other place it diverted was right here. This is Grand Coulee, right here. And it is grand. And here this map really gives a good indication. Upper Grand Coulee, Lower Grand Coulee. Now follow my cursor. This is the Coulee monocline. And I don't know what caused this, but you can see that the monocline is trending northeast, southwest. And then right here it takes this sharp right angle turn and becomes an anticline. And here's an anticline. Here's an anticline. And look at here. The anticline has been breached. Both of these have been breached by the Columbia. This is called Sentinel Gap right here. And it's a very impressive, awesome gap between the pieces of the anticline here. Then it flowed down, and down here is Wallula Gap, and all this ponding was right in here. Here comes the snake, which we talked about last episode. So we're putting these pieces together. And what I'm trying to get and hope comes out of this, though, is we're going to breach the walls of that box. Right? This color, this is taken from about 500 miles up. NASA photograph, pretty old, I mean decades old, but you can still see how clear. And you can see how there's a major discharge that when J. Harlan Bretz was first mapping this, he believed that the Telford, which is this one, and the Cheney-Palouse, which were this one, he didn't know about the existence of Lake Missoula. He didn't find out about that until like a couple of decades after he started his studies of the channeled scablands. He believed that these flows were discharging directly from the edge, from the margin of the ice sheet. He didn't know about the lake, so he wasn't thinking that there was this big lake, over here draining out, right? I think that his original concept was far more accurate and realistic than the prevailing model. I think that, yes, there were direct discharges from the ice front itself. Now you can see here, these are islands of loess, these lighter areas you can see, and then you have these lakes in here. Now those lakes are where the turbulent floodwaters scoured out troughs in the bedrock. And then after the floods finally drained away, it left this pooling in some of these over-deepened troughs. So you can see those kind of lakes running up here. You can see them here. You can see them up here. And then look here, you've got this channel. So this channel flowed from west to east, east to west. So this is called Crab Creek Coulee. I've made the traverse of this several times. On the floor of this coulee, you can see giant current ripples that are deposed in such a way that you can tell that the flow was from east to west. So you had you had so much water coming down here that even though you had a lot going down here, some discharged off to the west and then joined the waters of Telford. Up here, you have just the opposite. You have water discharging off the Telford, flowing here, and then ultimately flowing back, circling right around like this. The term for this branching system here that you see is called anastomosing. Anastomosing. And I looked up the origin of that word. A-N-A, anastomosing. I forgot what it means. I forgot the origin. I mean, I know what it means. I forgot the origin of the term linguistically. Anastomosing. Did you find it?
Yeah.
What does it say?
It's talking about, it's interesting, a surgical connection between two structures.
Okay, that's probably not the geological term.
But it sounds like similar.
Similar, yes.
In the form of it.
It's got to give you some more
origin is.
definitions, doesn't it? You could
it says the word anastomosis comes from the Greek word anastomosis, which means outlet or opening. The word is made up of ana, up, on, or upon, and stoma, meaning mouth. Early use of the word. Yeah, interesting.
Well, generally, if in the geological sense, it refers to like branching creek or stream or floodwaters.
A cross connection between adjacent channels.
Yeah, there we go. Okay. Cross connection between adjacent channels. So we see Telford Scabland, Crab Creek Coulee, Cheney Palouse Scabland, Snake River. This one, black and white, shows a little bit further west. So in this one, we can see Grand Coulee, Upper Grand Coulee, Lower Grand Coulee, right? What else we got here? You can see very clearly the Telford Scabland. Also, you can see the moraine lobe right here very clearly. This is called the Okanagan lobe. You also see that coming off the snout of the Okanagan lobe is this big, giant erosional feature right here called Moses Coulee, right? So you've got Grand Coulee upper and lower, and you've got Moses Coulee upper and lower. Both of those were gigantic discharge conduits for floodwater. Now, right from the beginning, I questioned the whole theory because of Moses Coulee. If you look at the downcutting at the top of Moses Coulee, it starts right under the ice sheet. See this gray arc, that's the terminus of the ice lobe. Let me see. Okay, I got a graphic here where I'm showing that very clearly. I'm showing the ice. So here's the problem. Way over here to the east is Lake Missoula. You got to get that water all the way down here. It can't divert down Cheney Palouse. It can't divert down Telford. It can't divert down the Grand Coulee, because if it did any of those, it's not going to get here. And clearly you see there's no channel cut here. Where is the route by which this water would have come that you can trace it back to the lake? Now, if I back up one here, let's see. Right here, right, you see this down here? Ken, these are anticlines. Here's a monocline. This is the Coulee monocline right here. And basically you're coming from a lower elevation and you're going up the warp, and then you're at a higher elevation. So water coming from here, once it gets to Grand Coulee, there's really, how do you get it? See, here's the top of Moses Coulee. So by what route did that water get from here over to here? There's no channel connecting it, right? Well, I went with Brad Young and our geologist friend, Jerome Lessman, and we explored all of this area here, all of this area up in here, the Omak Plateau, and we went up to the Fraser Plateau. And what we found was interesting. We found the evidence that the water came from down the Okanagan Valley, which is this right here. It's split. Right here where you see Omak Lake, remember I explained to you how the ice came down, and this was the original Columbia right here.
Right.
Then the ice blocked this, forcing the Columbia to cut across, take this shortcut across the basalt. Right? Well, so we went up and we found conclusive evidence that this is where the water came from. Not from over here to the east, but from the north. And I knew back in the 1990s, before I'd ever even visited this, that was the likely origin of the water. Right? So now, what's happened here is interesting. You see that there's this great flow, and if you actually go back to here, to this one, here is the coulee monocline comes down like this. If you follow the Okanagan lobe up, this was a great discharge of water following right along the edge of that ice lobe. It came down here almost due south, but then when it gets to the monocline, there we go, sorry, the monocline, what happens? You see it breaches the monocline right here. Now, it's about a 900-foot drop from the top of the monocline to the bottom. And it's about a mile wide, a little bit more than a mile wide right in here. What that meant was that when this flow first came down and hit the monocline, it spilled over, and it was a waterfall that was a mile-wide river, and the waterfall was 900 feet high. It was so erosive that it began to eat its way up current, and it created what's called a recessional cataract. And it ate its way all 20-plus miles up to the site of Grand Coulee Dam, where it is now. Now, this will make sense to you. You can picture if you've got flat rock, and then you compress that rock and cause it to fold, it's going to fracture and crack, right? Makes sense. Well, then what happens if you have fractured bedrock, that bedrock is going to be more conducive to being eroded. It's going to provide all kinds of places for the water to get in, and that's going to be, you can see that, look what happened. If you follow before the flood came through, you have the monocline coming down like this. So the water breached the monocline, flowed down, and some of the water was diverted off, and it scooped out the broken rock, and then that's what created Lower Grand Coulee. And then right here at the mouth of Lower Grand Coulee, you have this gigantic boulder field spreading out for hundreds of square miles with rubble from small, the size of, footballs, all the way up to the size of vans and SUVs and stuff. And I'm going to show you a picture of that in a minute. Okay, so you've got that happening. Now, furthermore, you've got another gigantic flow coming down the Columbia over here, an enormous flow. There's Lake Chelan that I talked about earlier, and I mentioned that at the terminus of the lake, it's a moraine dam. If you were to dig that moraine dam away, then this lake would drain into the Columbia and it would disappear. That's Lake Chelan. Okay, let's move on. We won't spend the time. I will introduce you to this guy. Joseph T. Pardee, with the U.S. Geological Survey, he was the discoverer of Lake Missoula. He published the first paper of his professional career on Lake Missoula in 1910. His final professional publication in 1942 was his second and only other paper on the subject of Lake Missoula. So he was a young graduate student in 1910, and first thing he discovered was the bottom of Lake Missoula had what appeared to be lake bottom sediments. Fair enough. Then he thought there was a lake. And he referred to some work by geologist T.C. Chamberlain from the 1890s, who had also theorized that there had been a lake in those valleys. He went the next step, though, and he found the high water marks. He found the Strand lines. So he wrote this paper in 1910, Glacial Lake, Missoula, and in there he documents his finding on the valley floor of what looks like lake sediments and his discovery of the Strand lines. Well, he continued to study it, but he didn't write another paper for 32 years. Why? Because his superior at the Geological Survey strongly discouraged him from doing that. So finally, when he retired from the survey, he wrote his second paper. This one was entitled Unusual Currents in Glacial Lake, Missoula. So he discovered something new that he didn't know when he wrote his 1910 paper. And that led him to the title of this 1942 paper, Unusual Currents. And yes, that's an understatement, that they're unusual. And I'm going to show you what he found that caused him to. I've been through there many, many times. And anyways, so there was this famous story that I'll save the details of it for another place, but there was a point where the geological community sent signals to Bretz that they were ready to give his flood theory a fair hearing. So they invited him to Washington to give a talk to this select group of elite geologists. And it was organized by this, what was his name? Younger geologist, though, who felt like he was going to make sort of a career out of discrediting Bretz and showing that, Bretz's theory of gigantic floods made no sense, and all the evidence that he was citing was actually formed over long periods of time incrementally rather than by gigantic floods. Galooly, James Galooly was his name. He was the one who sort of organized this event in Washington, D.C. They invited Bretz. They gave the impression that they were going to give a fair hearing, but in reality, the purpose of it was to pretty much discredit it and put it to bed and get rid of it. We don't need these giant floods. We got rid of the giant floods with Noah's flood in the Bible, right? Our science is now not being dictated by religious priorities anymore, right? So that was sort of the idea. Well, they get there, Bretz, gives his presentation. Probably nobody is fully convinced. Probably most of them are not convinced. Some of them may have questions, but in the group there was J.T. Pardee. He was there listening. At this point, Bretz did not really know about the existence of this giant lake. J.T. Pardee leans over to his colleague sitting next to him and whispers, "I know where Bretz's flood came from." That was a turning point, right? That was a turning point. It still took another 10 or 20 years, and younger geologists coming up to the profession that were more open-minded, and it took really up until 1969. I think there was a major paper published with Bretz as a lead author, but a bunch of other geologists. And it was like the confirmation, the final confirmation that, yes, a majority of us realize now that Bretz's floods are real. The controversies, such as they were, would have been on the specifics of the flood, how many, the origins, and all of this. Well, the next step in these flood studies came with Victor Baker, who published a paper in 1973. He had the background in hydrology, and he knew all the equations. He knew how to solve discharge. The letter Q stands for peak discharge. Well, Q, if it's a capital Q, it's peak discharge. So he knew how to use the basic formulas, the engineering formulas and the hydraulic formulas to calculate peak discharges. So he went into that Spokane Valley just north between Lake Pend Oreille and Spokane in a place called Rathdrum Prairie. And he found the high water marks, so he had the width of the valley. He knew the gradient, because it was sloping away from Lake Pend Oreille down towards Spokane. Those are the basic two. You need the channel geometry, you need the gradient, and you need the maximum water level. And then you introduce a coefficient into your equation that for the amount of turbulence. The smoother the channel, the less the turbulence. The rougher the channel, the greater the turbulence. Introducing turbulence into the flow causes a more rapid dissipation of energy. So anyways, he used the hydraulic formulas, and that's when he came up with that it was an unbelievable amount of water that had flowed through there, between 7 and 800 million cubic feet per second. So that's, like 20 times the combined flow of every single river on Earth from every continent. Now, so that was in 73. Well, then in around 1980, Richard Waite happens to visit this place in Pasco Basin where you see the rhythmites, and I'll show you. I think we looked at those, but I'll pull them up again. These are the backflood layers, and what Waite assumed, looking at that, was that each of those, and there were 39 exposed layers in this ditch. I've been there 4 times now. Last time when we were on our trip, Bradley was able to procure a private entrance into the property owners and took us down there because it's no trespassing. You can't just casually go in there and look at it. So Brad Young procured us right to go in there. The owners came down, and this was the second time we had gone down and visited this particular site where this big irrigation pipe in the 1930s, I believe it was, broke, and you had this huge gush of water that came out over this relatively soft landscape, and it quickly cut down this channel, this gully that might be 150 feet deep, 130 feet deep, something like that. And when it did, it revealed this sandwiching of these layers that are now called rhythmites. And they would be formed by backfloods. And we talked about that, how the stilling waters, once they settle in reverse currents, they'll leave a layer of mud behind, right?
Right.
So anyways, Pardee was there at that hit job, at that ambush, and this was the first signal of a turning point. Because now what the geological community was able to do is go, oh, well, wait a second, you mean, because, look, by this time, Bretz's evidence was indisputable, right? They've been fighting against this for a couple of decades, right? And now the evidence was so overwhelming that what they did, I think, was out of desperation. They said, oh, okay, well, we know that these outburst floods happen in modern times. We've seen them. We'll just extrapolate up from that and assume that it was a bigger version of that. Now we've got our uniformitarian explanation. It just happens over and over, and it's not that big of a deal. Of course, when you go out there in these landscapes and you're standing there looking at, these features, and you're boggling your mind trying to imagine. But let's go on. Okay, so we're gonna. Yeah, okay. This expresses the conventional view. It is now generally agreed that between 15,000 and 12,800 years ago, more than 40 tremendous deluges of almost inconceivable force and dimensions swept across large parts of the Columbia River drainage. They were the greatest scientifically documented floods known to have occurred in North America. Notice the date. Notice the last date, how close that is to the Younger Dryas. Right?
Very close.
Now, how do you get from this date to this date? Well, here's the assumption. Let's think this thing through. If each of those rhythmites represents a separate flood, okay, those rhythmites were in those basins where I pointed out that the water couldn't pass through Wallula Gap. So it ponded and drowned the basins in the areas adjacent to the gap. And then each time the water flowed out, the floor where where this gully is at about 400 feet, I believe. I've looked it up, 400 or 500 feet above the floor of Wallula Gap. So any time the water rose, say, above, and remember I said the water at its peak through Wallula Gap was just over 1,000 feet deep. So any time it was above, say, 500 feet through there, Pasco Basin was submerged. Anytime the water fell below that level, the ground surface would have been exposed. The assumption on the part of Richard Waite and the people who've come after him was that each of those layers represented a distinct separate flood. And each of those floods was caused by a separate damming. So in other words, if there were 40 tremendous deluges, there were 40 fillings and emptying of Lake Missoula. Therefore, there were 40 ice dams that failed and resealed the valley over and over again.
Over a 2,200-year period.
Yes. And so that period of time was, well, based upon the modern flow of the Clark Fork River, how long would it take to fill 600 cubic miles? And as I recall, in their equations, they didn't take account of evaporation, which, of course, as the lake increases in subaerial exposure, so is the evaporation. So I'm suspicious about the length of time that it would take to fill Lake Missoula to full pool. But in either case, 50 to 100 years. So if you got 40 fillings at 50 years each, that's 2,000 years, right? Now, there have been other datings that have put the earliest floods older than 15,000 years. And I'm suspicious of those dates for a number of reasons, which we won't go into here. But it has to do with the fact of what I think may have been the potential ultimate trigger for the great meltdown, if you want to call it that. David Alt, in his book Glacial Lake Missoula and Its Humongous Floods, which is a book I recommend to people who are going to go on the tours or anybody who wants to learn more. He says Glacial Lake Missoula was among the largest lakes ever impounded behind an ice dam. Well, yes. The ice dam broke when the water behind it got deep enough to float it. Each time that happened, several dozen times, the lake dumped a catastrophic flood on eastern Washington and the Columbia River. Those lakes and floods are among the largest of known geological record. And here's just another graphic to kind of give you the geography of the flood. You got the ice dam. You've got the lake. You've got the scablands. You've got Wallula Gap. You can see that showing here, this was one of the problems I have with the ice dam model, right? So you've got this discharge that looks like it starts right up here, west of the Okanagan Lobe. So you got to get this water here over to here. To me, it's just a whole lot more straightforward, Bretz's original idea, that each of these areas here is discharging right off the ice sheet. Now, obviously, if you remove the ice dam and this water flows out, yeah, it's going to flow out and it's going to go down the Spokane Valley and discharge right here. Absolutely it is, no question. But then it becomes problematic when you try to explain it Grand Coulee Dam. Because look, remember I showed you the monocline was 900 feet higher. So that would mean the water has to come here from the east, and then it has to go up over the monocline. See? And then what's it going to do? It's just going to run into the wall of ice. Well, let's just keep going here. So there you see the Idaho-Washington line. Here's the Idaho-Montana line, and they're showing the ice right here, stopping right at the state line. Now when we go on tours, there's a place right here, the dam. There's a dam right here with an overlook, right where they say the ice dam was. Okay, so on my first trip out here in '98, I looked up. I called him before I went out. I looked for what geologists have done the most work up here in the area of the ice dam and up and down in the Clark Fork Valley. And it was His name will come to me again in a second. It's not that important what his name was. It will come to me. But so I actually went and visited him at the university there in Moscow, Idaho, and went up to his office and lab and interviewed him for about an hour because we had not yet gone up. I had not yet made my first traverse up the Clark Fork in '98, but I made my first within a day or a couple of days after meeting with the geologist. And what I wanted to do was I wanted to talk to him about, well, where was the ice dam? Now, typically, I know enough about glaciers to know that there's a marginal profile, right? And if there's water lapping at it, well, then icebergs will break off, and you couldn't get a shear wall. You could, right? But I wanted to know right where the ice dam was. I said, I want to go find the point right there where I can be going, okay, there was the lake, there was the ice dam. He couldn't tell me because he didn't know. And by the end of our conversation, it wasn't James Teller. The end of our conversation, he's kind of expressed something to me, and I wished. One of my great regrets is I had no means of recording it at the time. I didn't even know if I was going to be able to connect with him because when I first went up to his office, he was somewhere else. So I waited like 20, 30 minutes for him, and he showed up. And I said, hello, Doctor. It's right there. It starts with a B. Anyways, so he was gracious enough to invite me in, and we had a very great conversation where he said to me he didn't really know what I could tell. Basically, he was not convinced that this model made sense. So I went away from there confident that I was on the right track. Went up there. I've made, half a dozen traverses up and down through the valley here. When Pardee wrote his second paper in 1942, he did a study right through this area right here, which is a narrow gap. And so what you're trying to do when you want to figure out discharge, you got to find a stretch where the conduit doesn't change a lot, right, from one end to the other. You know, it can't. You don't want it to change gradient steeply because that changes everything. You don't want it to, widen out, narrow. What you're looking for is a consistent valley width. So that's what he found right in here, in this narrow eddy narrows. It's called eddy narrows, and we're going to look at some pictures. We're about to get to the pictures here now. We'll leave it at this. You can see here now, hopefully you can identify. Here's Moses Coulee. Here's Grand Coulee. And here's the Coulee. You can see the Coulee monocline is right in here. And right here at the south end is Soap Lake. And that's where we stay when we do these tours out there. There's a resort there, Soap Lake Resort, right at the mouth of the Coulee. Yeah, so here this expresses the attitude that became Robert R. Curry, 1977, Discussion in Glacial Geology of Flathead Valley and Catastrophic Drainage of Glacial Lake Missoula. And this is, you can see here what they're really trying to do. Erosion of the channel scablands thus becomes a more geologically reasonable consequence of the existence of outburst flooding near Pend Oreille, Idaho. It is really rather remarkable that it has taken the geological community this long to develop this picture of Lake Missoula floods, particularly due to the long-standing and highly controversial history of investigation of the channel scablands. Many highly creative, productive scientists have devoted an enormous number of publications to debate and elucidate these flood features. Particularly perplexing has been the lack of recognition of the possibility that the Purcell Trench ice dam would behave just as do other ice dams around the world. It now appears that, except for scale, the Lake Missoula floods are really a rather typical example of what is probably a rather common geological phenomena during times of maximum glacial advance. And this became the mindset. Oh, it's except for scale, except for, that's nothing. Scale means nothing, right? Except for scale. It's just as we do other ice dams that we've seen them in Alaska, we've seen them in British Columbia, we've seen them in the Himalayas, we've seen them in Iceland. There's no reason why we should imagine that this is anything special or unique. This became the dominant view of the whole phenomena. And within that, that box kind of encapsulates the thinking. We don't go outside that box.
Stay in there, yeah.
Stay in that box. Yes. So this one's interesting. Oh, there it is, Breckenridge. Roy Breckenridge. Remember I said B? I had this B.
Yeah,
That's it,
yeah.
Breckenridge. Roy. Sorry, Roy. Didn't mean to forget your name, man. He's gone now.
Rest in peace.
I know. J. Harlan Bretz proposed in his own words an outrageous hypothesis that the erosional and depositional features in the channel scablands of eastern Washington were produced by catastrophic flooding. At that time, Bretz could not adequately explain a source for the floodwater other than to speculate upon a combination of events that included rapid melting and ablation of glacial ice combined with torrential rainfall. Now, I would argue that Bretz's original conceptions were far more realistic than the later paradigm. But then we have to, of course, look for an agency that could cause rapid melting and ablation of glacial ice and torrential rainfall. However, then John Elliott Allens and Marjorie Burns, in their book Cataclysms on the Columbia, said this: by 1925, after having published 4 papers on the scablands, all that Bretz could suggest as justification for his sudden and voluminous deluge was the possibility of increased runoff from glacial melt, from water welling out along the edge of the Cordilleran ice sheet and draining away across the southwest tilt of the Columbia Plateau. But the runoff Bretz proposed wasn't enough. Nothing but prodigious amounts of water could have formed the scablands' scarred and channeled features, and it was hard indeed to conceive of glacial melt achieving such a level of flooding. See, it's beginning. Yeah, and I would agree with that. Yes, it is. It's very hard to conceive of that much glacial melt. And this is why it scared the mainstream people away. They didn't want to go there. What if we did say that there was glacial melting on levels sufficient to trigger this flooding? Well, then what happens to glacial Lake Missoula? And how do we explain? Because, for one thing, in order to convert ice to water requires energy, doesn't it? Requires the input of energy. So then that raises the question of, well, where does the energy come from? Puzzles were added to puzzles. If the flood had resulted from excessive glacial melt, how could such a sudden, intense, and temporary melting be justified? An explanation was required, and Bretz, for lack of anything better, offered 2 rather far-fetched possibilities, improbable ones, but the best he could contrive. Either there had been a sudden and extreme but short-lived softening of the harsh Ice Age climate, or a gigantic Yokalaup had occurred, an underglacier surge of ice-melting heat caused by volcanic activity. Both possibilities would have greatly increased the glacial melt-off, but, as Bretz well knew, there was no evidence that such climatic or volcanic events had occurred. Now, let's amend that last underlined statement. Yes, it is agreed that there's no evidence that volcanic events of sufficient power and magnitude had occurred to trigger this melting. However, as we now know, there have been 2 extreme warmings of the climate bracketing the Younger Dryas, right? And associated with 2 gigantic meltwater pulses into the global ocean. It's there. Independently, there had to have been some climatic event to have caused meltwater pulse 1A and meltwater pulse 1B. Because the meltwater pulses, the rapid rising of sea level, is a direct evidence of rapid melting. Well, Glacial Lake Missoula model does not connect or explain any connection between rapid melting of the great ice sheets and catastrophic flooding. Pardee, 1942, published the results of his Lake Missoula study. He introduced evidence for an impoundment of 500, now it's 600, cubic miles of water behind an ice lobe that crossed the Clark Fork River in northern Idaho. Other evidence indicated that the ice dam had suddenly failed. Now we'll get to what that other evidence is, releasing the impounded water. The water source for the catastrophic flood was no longer a problem. Yeah, we got it. Just a big lake. There's no reason. It's just not another typical. It's just bigger, but it's what we see. See, you can see what's happened here. We've got it explained. No problem. We've solved the problem here. Well, we solved the problem by, only looking through a narrow lens. We'll skip this. Okay, so here is Missoula Basin and Mount Jumbo and Mount Sentinel flanking, right here, Mount Jumbo and Mount Sentinel flanking this valley right here, right outside the University of Montana campus there, right? So if we go there, you can see Mount Jumbo. You see the strand lines?
Yeah.
Yeah. Yep, there they are. I like this one because this is an old photograph, black and white, but you can see very clearly the snow that is accumulated on the strand lines because each of those was temporary shoreline. Now, here's the question. Do each of those strand lines represent a separate lake, or is it the draining of a single lake? Now, the draining, remember, picture in your mind the map of Lake Missoula, how intricate and complex it was. It's not going to be like draining a bathtub. You just pull the plug on one end and everything moves. You've got to go through constrictions, expansions. You've got to go around 180-degree turns. All of that is going to be causing a loss of energy, a slowing down of the water. So I'm just showing here strand lines left over from a single outburst draining of ice lake in Alaska. So here's the ice, here's the lake, and this is all moraine that you see here. And then once the lake drained away, you can see see the lines? Mm-hmm. Yeah, it's left strand lines behind. Same thing here. This is Lake Como, western Montana. Strand lines formed as lake level dropped during a drought. This is not the result of the lake filling and draining multiple times. It's a single draining of the lake. But it was not consistently uniform over the whole process. It stalled at various elevations, enough to etch a shoreline. There may have been a small rain or something that accumulated or whatever. But yeah, you can see here very clearly strand lines, and they are not yet within the mainstream view. Each of those shorelines is now associated with corresponding to one of the rhythmical layers
And how many strand lines are there on Mount Jumbo?
They've been counted. I counted them at one time. I don't remember. Let's see. That looks like the top one right there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Probably 30 or 40. That's a good question. Very good question. Okay, so now we're going to get to what led Pardee to call his paper Unusual Currents. So here's Flathead Lake, and this shows roughly the configuration of the ice at the end of the Ice Age. So you can see where Flathead Lake was under the ice, right? And right here at the south part of it, right in here, this is moraine. It's called the Polson Moraine. And it's hundreds of feet high, hundreds of feet thick. It's named after the little town of Polson right here. And this is the Flathead River draining. It cuts through the moraine right here and drains out, flows down around here, and then joins the Clark Fork. Now, when the floods occurred, you had a major discharge down this valley right here. And then the water did a hard left turn and went south, flowed down here, and then it hit this rim of hills right here. And it overwashed the rim of hills and pushed out a massive deposit of material in this basin, which is called Camas Prairie Basin. Camas Prairie Basin. It was undoubtedly augmented by flows coming off of these lobes here. Right here, there was a meltwater flow that came off of this lobe that entrenched into thick layers of alluvium that covers the whole floor of this is called the Mission Valley here. Okay, so let's go to the next slide. And we're just a little further south. You can see here's Camas Prairie here. Here's Camas Prairie. And it has a discharge point here at the south where any water flowing into Camas Prairie would flow out through here and join the Clark Fork. However, there's also a mountain pass here called Rainbow Lake Pass that was submerged. And you're going to see this all taking shape in a second here. So here's the names. You have the Little Bitterroot Valley here, Rainbow Lake Pass, Camas Prairie, Clark Fork River, Mission Valley, Flathead River, and the National Bison Range. So whenever we go on our tours, we usually stop there for an afternoon of bison tipping. Similar to cow tipping, but a little bit more challenging. All right, beautiful Mission Valley, view to the south, Mission Mountains to the east, right here, going back. Here's the Mission Mountains, right? So what this is doing, it's the same landscape. It's now showing water flow routes, right? So water flowing out of Camas Prairie here, water flowing around this big protuberance knob here that's the Bison Range, flowing around both sides of that. This is there's an incredible viewpoint at the top of this where you can look up the whole Mission Valley and you can see Flathead Lake in the distance. It's a hell of an impressive vista. Anyway, so that's what these blue arrows are showing is water flow. Okay, so here's the south end of Flathead Lake looking north. Serene Flathead Lake at dusk from Polson. Looks nice, doesn't it?
It does.
It is nice. Here's Flathead Lake. Here's the Flathead River. Remember I just said it's entrenched deeply into these thick, hundreds of foot thick alluvium. This is the outwash stuff.
Wow.
Right? It's massive amounts of this. And it's relatively unconsolidated. And look here. Inside bend of the meander, you've got this big terrace. Remember what you learned about Tammany Bar? Right? Erosional on the outside of a meander, depositional on the inside.
Yep,
right?
It's washing up.
This is a meander right here. And at this point, the Clark Fork the Flathead River is pretty much entrenched into the alluvium substrate. But let's say you had a big modern flood and it overspilled right here, because this is oftentimes how you get a cutoff meander. Like you look in the southern part of the Mississippi River Valley, you see many examples of cutoff Note the underfit condition of the modern Flathead River. In other words, here's the river and here's the channel. The channel was created by a much bigger flow than the modern river.
Yeah.
We'll just keep going here.
During that the deposition, is that what we're looking at on the previous slide?
What's that now?
So this is, I believe we looked at this picture before.
I think we have glanced at it without any discussion or explanation.
It looks like this is where some of these boulders were deposited.
Yes, and notice here, the boulders are tilted toward the south, the flow direction of the modern Flathead River. They show evidence of large-scale outburst floods issuing from the Flathead lobe of the Cordilleran ice sheet. Now see, what I would argue is that this, okay, here you go, flow direction. What I would argue is that this is evidence of the filling of Lake Missoula coming from the north, flowing to the south. Down an amazing long linear feature trending north-south called the Rocky Mountain Trench. During the last great glacial advance, the Flathead Glacier moved down the Rocky Mountain Trench, depositing the Polson moraine at the south end of Flathead Lake and various smaller moraines in the Big Arm embayment. Near the middle of the lake, the southward moving Flathead ice split into two parts. One lobe continued south into Polson Bay, the other turned to the west and moved into Big Arm embayment. The Big Arm ice split again into three sublobes. These in turn pushed into the Dayton, Big Draw, and Big Arm valleys. The three sublobes deposited terminal moraines in each valley, moraines which are believed to be of the same age as the Polson moraine. Let's go back to this. There. So, you see when it's split into these three lobes. And each lobe deposited moraine.
Mm-hmm.
This is the Big Arm embayment, it's called here, and this is called Big Draw. And there's the highway, I think, what is it? I forget the highway number here, but there's a highway that goes through Big Draw. So on the tours that cover this part, we go down through here, and we follow the route of the floodwater down along this highway. And then right here we come through this pass, right? It's called Marco Pass. And when we emerge at the south end of the pass, there's a pull-off where you can strategically view the whole Camas Prairie Basin to the south. Okay?
This is just a hell of a story, Randall. I'm just trying to piece my thoughts back together here.
Well, wait till you see what's coming. We're just getting into this.
We're just getting started. We might need another episode for this then.
Well, yeah, I think we should because, yeah, well, you'll see as we proceed on here, the questions. I think you will begin to, as it unfolds, you're going to get questions. And then you're going to realize that the only way to answer those questions is we definitely have to expand to the big picture. For sure. All right, so we're seeing this graphic right here, aren't we?
Yes.
This is where we had those three lobes that I showed you.
Mm-hmm.
Right? Three of them that kind of
right.
spread out. So we had, this is called the Big Arm embayment right here. Yeah, there's the Big Arm embayment. So you can see right here, kind of trace out the margin of the lobe. This is the moraine right here. And here's where that breach occurs. The highway utilizes that breach through the moraine. But there was something else going on here. Here was another lobe that came up this way and terminated. And then you had a major flow. It looks like it came down this way here. Maybe came through. It might have come under the lobe here, but in either case, it looks like you had a major flow convergence starting right here. And it came down and flowed, and then it breached this ridge that came down that was originally probably connected with this island. But it breached this ridge right here. At the time, we know that the ice sheet was here, the Lobe, because the water was diverted to the west. It didn't flow right down here into the Big Arm embayment. It was diverted around this way and discharged down here, and the water diverting around the Lobe here joined the water coming from under the Lobe here, and it flowed down Big Draw to the west. So this is just showing scale invariance. Notice there the delta type fan, how it fans out.
Mm-hmm.
And also notice that this channel through the sand here, that's like Grand Coulee. Right? So this is a major piece of evidence that contradicts the, several lines of evidence suggest that Dayton ice lobe, this is the Dayton ice lobe here. That's the Dayton ice lobe.
Mm-hmm.
And there's several lines of evidence suggest that the Dayton ice lobe impounded a glacial lake in the upper Dayton Valley. This lake, termed Glacial Lake Ronan, was centered approximately over the site of contemporary Lake Mary Ronan. Now look here. That's this lake right here. But it would have been much bigger impounding of water. Okay, so where did that water come from? Okay, well, get here. Smith, in 1966, believes that the glacial lake attained the following dimensions: surface elevation 3,880 feet, the greatest depth 322 feet, that's a deep lake, surface extent approximately 22 miles. On the mountain slope 2 miles west of Dayton, a small high-level bedrock cliff and bench are cut into the slope at 3,880-foot level. These are believed to have been cut by water from Glacial Lake Ronan. However, and this is the key point, since erratics have been found at elevations up to 4,200 feet, Glacial Lake Ronan must have at times risen to a considerable height before an outlet was established. So you have erratics that are up at the very highest water level of the lake, right? What are those erratics doing there? When we find the erratics down current, like scattered over the scablands, they're 1,000 feet lower. They're hundreds of feet lower, several thousand feet lower. Here you have an erratic that's sitting at the very height of that water. What's that water going to do? I mean, it would, in other words, it would have to go higher to float an erratic or to put an erratic there, unless it's totally the result of glaciers, right? So in the study,
just to understand, it is 400 feet above what they thought the highest point of the shoreline was. Surface elevation of 300 or 3,000.
Erratics have been found at elevations up to 4,200 feet. Well, that's the highest water mark.
Okay,
so clearly those erratics were not emplaced by the water of Glacial Lake Missoula. Either they were emplaced by iceberg transport or directly by the glaciers. And that can be determined. It's going to take some field work. But I'm going to predict that that their origin was from the Canadian Rockies, and they were carried south on floodwaters that were oftentimes flowing higher than the highest level of Lake Missoula. In other words, if you had waters flowing at 4,500 or 5,000 feet, that's going to be above the high water mark of Lake Missoula. Yet in the current models, you didn't have any flooding. That was the highest the water went. So when the lake drained, all the erosion and deposition would have been below 4,200, see? Then in the study area, the latter part of the Ice Age was also a time of impressive erosion by meltwater flooding. As the waters of glacial Lake Ronan drained away, a conspicuous 2-mile zone of rugged cliff and bench topography was cut into the eastern slopes of the Hog Heaven Range, 2 miles northeast of Elmo. This steep terrain culminates at a 500-foot high Chief Cliff, a prominent local landmark. Let's go back to this. And right here, if you look at my cursor, there, this is what he's talking about, this right here. And Chief Cliff is right here. And I've got photographs of Chief Cliff to show you. The Chief Cliff topography originates near the Big Meadow in Dayton Valley and continues around the eastward-facing slopes of Hog Heaven Range. So this is the Hog Heaven Range right here. Okay. Alden believed that the waters impounded behind the Dayton ice lobe escaped between the glacier and the mountain slope. Thus, a temporary spillway was eroded at the base of Chief Cliff and produced what Flint terms glacier margin channels. So let's that's all my writing. Okay, so there's Chief Cliff, 500 feet high, right? Now, look at this outcrop here. Pre-flood, imagine this is continuous across here. And you're looking at, this is what Flint is referring to as a, what did he say, an ice marginal, glacier margin channels. Okay, we'll see that. Here's the cliff. And all of this down here is gigantic masses of huge gravel deposits, right? This is from the north looking to the south of Chief Cliff. There we are about to get into a small airplane to go up to have a look. When was this? This was early 2000s. So this is our pilot here. So ice marginal. Here's the margin of, how do you pronounce that?
I don't know.
Brida Mercurial something.
Brida Mercurial. That sounded about right.
That glacier in Iceland with a small ice marginal meltwater stream right here flowing alongside and under the edge of the glacier right over here. So now what I'm going to do is I'm going to just show a cross-section of if you had a lot of meltwater coming through here. So here's your glacier margin. On one side you've got the hill or the mountain. On the other side you've got a glacier. So if the glacier melts away, you're only going to have one side of the channel, aren't you? Mm-hmm. Okay. And then the water flow increases. Now check this out. Here's Chief Cliff. Follow this line right here. Okay. So now all of this was under the lobe. All of this was under the lobe, and this is that glacier margin channel right here. So I've done a very crude graphic to show the pre-glacier profile, then the glacier, the Elmo sublobe. So all this is glacier to the north. You've got the sublobe here, and then this ice glacier margin right here became the channel, water flowing towards the view here, and then the formation of Chief Cliff. So the ice here provided the east wall of the channel, and the cliff was the west wall. So that ice, that water flowed here, but this lobe came in this way. So when this water hit the lobe, it couldn't spill directly across. It was diverted to the west. Does that make sense?
Kinda.
The same discharging waters which eroded the Chief Cliff terrain carved a spillway into bedrock along the north side of the Elmo Basin between Hog Heaven Range and the Elmo Lateral Moraine. Well, look, imagine it this way. So there's this ice lobe, and the water's coming from this way. Well, it hits the ice lobe, and then has to divert.
Right.
See? And that's what it did. That's what this blue line is showing here. The water came from up here and wrapped around the cliff. All of this area here was under the lobe of ice.
Yeah, okay. So on the right, if you were to put your mouse on the right side of that picture, that's where it's hitting the...
Yeah, over here you've got the big lobe of
glacier.
ice coming in, and it stops right here. Well, and actually, it's hard to say because of the amount of erosion. But this was the trough here, and the ice came up here, and then all of this in the foreground was under ice, right? Probably higher than the cliff. So when that water came, it got the ice diverted it to the west. And all of this right in here are big piles of gravel that were dumped. There's a huge gravel quarry there now. So the same discharging waters which eroded the chief cliff terrain carved a spillway into bedrock along the north side of the Elmo Basin. The spillway consists of a network of deep interconnecting channels having a gently westward inclination. Its width varies from 200 to 2,600 feet, and it extends for 4.5 miles from Chief Cliff to the north end of the Elmo Moraine. So that what he's talking about is this right here. So you can see the moraine. This is where the lobe came. Follow my cursor, right? So when that water came down through here, it carved Chief Cliff and hit this lobe of ice that was right here. And then it diverted to the west and came down this way, carrying an enormous amount of sediment. Deep accumulations of gravel outwash on the floor of the Big Draw indicate that an immense volume of sediment-choked meltwater once discharged down the Big Draw. The Big Draw outwash, varying from 1/2 to 1 mile across, extends westward for 8 miles from the Elmo Moraine. And here's an aerial view. So this is what it's talking about. That's the deep accumulations of gravel outwash is why the floor is flat. Now, if you could come in with a big broom or a giant pressure hose, what you would see here is that it's probably 200 or 300 feet thick. And if you were to wash it all out, you would have a sort of a V-shaped valley here, right? But it's been filled up with all of this outwash. Now it goes down here, and then it diverts to the south, right down here. It wraps around these hills and diverts to the south. And here's the highway through there. And here's a map, again, showing here's the breach. This is the Elmo Moraine right here. So you had a flow coming down this way. You had a flow through the breach. And then you had this enormous amount of sediment outwash that made this flat floor. And it sculpted these mountainsides here, which you will see. So here's your water flow. And here's the mountainsides. You see this? There's the flow direction. Look at this. And then you look at the flat floor here. This is all, imagine 200, 300 foot thick layer of mud just being dumped in on the valley floor. Then the water came down and it wrapped around, and you'll see here, like this. And then what do you see on the hillsides where the water wrapped around? Strand lines. Yep. Then the water flowed down the Little Bitterroot Valley here to the south. Here we go, down south. And then it hit the Marco Hills right here. So you've got this huge flow coming down, and then you've got this hill transverse obstructing the flow. The flow hits the hills, washes over the tops, breaches them in several points, and then all of this outwash that it is carried down into Camas Prairie Basin right here forms the big ripple train. So this area up in here, this is what the passage of these giant catastrophic floods do to the landscape. And then down here you see the Marco Hills stretching across from east to west. The water hit that, then overtopped the hills. Camas Prairie, this is Pardee now talking in 1942. Camas Prairie is distinguished by a number of unique ridges that have the form, structure, and arrangement of ordinary ripple marks, but are so large that the term ripple mark seems inappropriate. It is retained, however, for want of a better one. Except for a few inconspicuous ones below Big Creek Pass, the ridges are grouped in belts appended to the other three northern gaps, namely Duck Pond, Marco, and Wills Creek. The locals call it Marco, so I call it Marco.
Okay.
A relationship suggesting formation by currents entering the basin through those channels. The ridges range from 1 foot or less to 50 feet. That's a 5-story building in amplitude, and from a few feet to as much as 500 feet in wavelength. So here's Camas Prairie, right? Here's the Marco Hills, and here's the 3 passageways that it referred to into Camas Prairie. There was one diversionary passage through Rainbow Lake Pass here, and then the main discharge outlet was here to the south. So here's current rippled sand deposited on the floodplain of South Fork Peachtree Creek after Hurricane Ivan flooding. The floodplain is now occupied by Medlock Park. It had been decades since any flood had overtopped the modern banks of the creek. But this hurricane that came through, the creek, which is over here in this brush, rose up out of its channel and spread out over the modern floodplain and deposited this layer of sand. And so here you can see measuring tape shows the chord length and the amplitude of the ripples. Now, I was able to look on trees and nearby buildings and determine the high water mark. There was a high water mark on the buildings. It was just almost 24 inches above the ground. So you had a flow of water from right to left. Yes, from right to left. And you can see the chord length. There's 2, there's 5. So 3 inches, typically, chord length. Amplitude, about 3/4 of an inch. So this is water 2 feet deep. Okay? Now, as we're looking out, Camas Prairie, we're looking out. You don't see them that well here, so let's find a better view. Let's see, Highway 26 crosses the view. Here's Highway 26. This is a farm here. So the water coming from the north spills over the hills. Here's a huge fan delta. Now you can see ripples coming out this way. You can see, in fact, you can look at the ripples, and the ripples diverge from each of those 3 outlets that we saw. That's Duck Pond Pass, Marco Pass, and Wills Creek Pass. Mm-hmm. So look at the size of these ripples here. You had a secondary ripple train here and another ripple train over here. Let's see, I probably took this from aerial view. So here you have a fan delta, and then you can see the ripples. See the ripples?
Mm-hmm.
Look at the floor of the valley. Look at the floor of... So this is what Pardee discovered and wrote about in his 1942 paper, was the presence of these giant ripples.
And what is the amplitude of those?
Well, they're up to 50 feet high.
50 feet high. Oh, wow.
Yes,
okay.
50 feet. Yeah, 50 feet. Well, yeah, let's see. What are we looking at here? Well, yeah, I mean, this thing here, that's the height of a 5-story building right there.
Oh, my gosh.
Yeah.
So 3/4 of an inch, if we wanted to scale this up, 3/4 of an inch is based off of a 2 foot deep water.
Yeah. Well, I can tell you how deep the water was through here. So let's see what your calculation comes up with.
Okay. You said 2 feet deep water?
Yes.
1,600 feet deep?
Not quite. Well, the floor of the valley is right at about 2,800.
Okay.
Remember the high water mark?
Yeah.
42?
4,200. Yeah.
So 1,400 feet deep.
Okay, so close, but not
Close, yeah.
Yeah.
1,400 feet deep. 1,400 feet deep. Now, at this point, the valley is 5 miles wide. So imagine a river 5 miles wide, 1,400 feet deep.
I can't.
Well, this is why Part E saw this, what we're looking at right here, and called them unusual currents.
Now I'm getting why they were so unusual.
Yes. Yeah. Well, you have to kind of stick with the story a little bit to start really putting the pieces together and getting the big picture.
Mm-hmm.
Yeah, so this is aerial shots that I did probably, I don't know, early 2000s, I guess.
There's so many different examples is what we're going through of the scale of this.
Yes. This is looking north. So there's your big fan delta right up there. So that's the stuff that's splayed out from, I think it's from Marco Pass. And here's looking down on the fan delta, and you can see, look what's on its surface. Okay, so view south over the Wills Creek Deltaic Bar. State Route 382 is visible across the upper right-hand corner. Oh, okay, so that's this up here. And this is a farm, you can see right here. There's a farmhouse there, a 2-story farmhouse, which is kind of lost in the whole landscape. So this is the composition of a Camas Prairie ripple. Now, do you remember imbrication? Did we talk about that? The tilting of rocks. This is imbrication, where you see the tilting of the rock. Here, the tilt is in the direction, the downflow direction. So you're looking at a cross-section of a big ripple here. This is at a road cut. And flow is from right to left. So here we are looking west. Here's the Marco Hills. And, oops, I want to call your attention to this feature right here. That's Rainbow Lake Pass. And you can see Rainbow Lake Pass is higher than the floor, where the ripples are. Water flow is from right to left. Okay, like this thing right here, this is a huge fan delta splayed out from one of the passes. That's probably Marco Pass. Then there's another one here that's highly eroded. But Rainbow Lake Pass, I think we've got the next one. There's Rainbow Lake. Looking east, current flow was toward the viewer. All right, so here we go. So here's Rainbow Lake and Pass from the air is viewed to the northwest. The lake elevation in the pass is 3,590 feet. So right up here is 4,460. So if we go 4,200 minus 3,590, we get 600. So the water at its maximum was 600 feet deep moving through this pass. Then as the water level dropped in Camas Prairie, then you can see that the floor of this was above the floor of Camas Prairie. Right? What did I just say here? 600. So 700, it's still had to get down. It was 1,400 feet deep. So right here it was, say, 600 feet deep. So that means once it had dropped to where the water was 800 feet deep in Camas Prairie, then this would have been isolated. It no longer would have been a spillway. It only was a spillway when the water rose up to 4,200. And it undoubtedly cut a lot of material out of here. But once the water level dropped and was below 800 feet deep, then this was left isolated. And the flow through Rainbow Lake Pass would have stopped at that point. And all of the flow out of the basin would have been through that southern outlet. Does that make sense?
Mm-hmm.
Yeah. So at its peak, it was like 600 feet deep through here. And here's 4,200. That line represents 4,200 feet. So there you can see over here, that would have been 600 feet above the floor of Rainbow Lake Pass, and then it would have been another 800 feet down to the floor of the basin.
Yeah, I see.
And that would have been... Yeah, Rainbow Lake Pass exhibits strikingly the effects of a former large and rapid westward flowing current. Above the lake, the floors of both branches have been severely scoured, exposing the bedrock, which remains bare. The floor is furrowed with channel depressions, several of them holding ponds or marshes. Upstream angles of prominent knobs are slightly rounded as by water, and so forth. These features apparently were formed by a huge current swinging from side to side as it moved swiftly through the pass, eroding the outsides of bends and depositing gravel bars on the inside. A huge current. I mean, can you imagine a huge current 1,000 or more feet deep? So there's... And here I've done the elevations of the floor. And then National Bison Range, what do you see? Shorelines, strand lines. Yep. We'll skip some of this. Remember I talked about Eddy Narrows? Eddy Narrows was that constricted valley, long enough that's where Pardee did his calculations of peak discharge of the draining, and he came up. Remember now, Vic Baker came up with 700 to 800 million cubic feet per second. Pardee calculated through, this is an Eddy Narrows right here. He came up with slightly more than that. I'm sorry, slightly more than half. So his was about 9.5 cubic miles per hour. Now, if you look at this, you can notice something. You go up, you've got the sheared rock faces, then you get up here and you've got full, thick forest growth. Mm-hmm. This is the high water mark right here. So this is where the water reached. And everything below is just scoured, sculpted rock with little patches of greenery, of trees, sort of. But then above you can see the full forested area. So that's your high water mark right there at about 4,200 feet. And then as you go through, cliff face along the north side of the Clark Fork River, scoured and etched by the Missoula flood. Flow was from, flow was from right to left. Cliff face along the north side of the Clark Fork River, scoured and etched by the Missoula flood. Flow is from right to left, and just for scale, you see the little guy standing there.
Yeah.
So look at the face of this rock. This is not smooth. This is etched, scoured. This is scoured. That would be the word. Flow right to left. So this is you learn to look for things like this when you're tracing this out. Clark Fork River and Valley near the supposed location of the interface between glacier ice and Lake Missoula. Now, remember the discussion about the main valley and trunk valleys coming in and backwash moving up the trunk valleys? So one of the valleys, tributary valleys of on the Clark Fork, that's where this is. So we were able to go up. So Clark Fork is down here. So imagine you've got this big backwash, almost like a tidal bore, coming up this way through the tributary, and then it backfloods, and this is its deposit it left behind that I'm standing on when I took this picture. So this is from above. So this is where we're able to go up the tributary valleys, find the depositional evidence that was how far it got, backflooding up the tributary valley. Then it turned around and flowed back out. So this is from below looking at it, and this is standing up on it. And then other tributaries have finer grained stuff like this. White Pine Gravel Pit. You see the man standing here for scale. Now what's interesting about this, if you'll notice that the strata you see here, they're sloped. They're not flat. Remember now, when you have this kind of deposition, what are called foresets, the downslope is in the direction of the current. So current here was from right to left. See the tilt?
Yeah. Right to left.
Okay, now here was, this is Roy Breckenridge. Now notice this is 1989. So I had this field trip guidebook when I went out there, and I interviewed him in 1998, right? He had written this paper. He says, the White Pine Gravel Pit is located approximately 3 kilometers south of Highway 200 on the White Pine Creek Road. The deposit is about 100 meters above the valley floor, so about 330, 340 feet. The gravel pit presently exposes over 50 meters of gravel section. This feature is located at the mouth of the tributary valley and trails southeast from the valley side in an opposite direction to the present Clark Fork River and the flows emptying Glacial Lake Missoula. Directional indicators show that the feature was deposited by currents moving in a southeastward or up valley direction. Now, what's the significance of that? Well, here's another example. So here you're right in the area of the ice dam, Dry Creek gravel pit. So I visited this gravel pit multiple times. And look at this. Now, a couple of things that are interesting here. Number one, they're quarrying this gravel. But I want you to look up here and imagine that you're 100 feet into this forest. You're walking along on the forest floor. You're a hunter, whatever. You're a hiker. You're a camper. You're walking on this forest floor. And you have no clue what's actually under your feet. If you dig down, you get this. Look at this. That is sediment-choked floodwaters back-surging into these tributary valleys, dumping this stuff. But the problem here is this. So this gravel deposit at the mouth of Dry Creek, the landform trails southeast from the valley side in a direction opposite that of the flow of water that emptied Glacial Lake Missoula. Now that's a problem. That's a big problem. This pit is at an elevation of 817 meters, more than 125 meters above the floor of the valley. The foresaid beds are several meters high and dip eastward. Clasts, that is, rocks within the matrix, are poorly rounded and some cobbles striated. Although most clasts are Precambrian belt metasediments derived locally, some clasts of granite and diorite exposed in and adjacent to the potential trench are present. Granite and diorite, where did that come from? Now, all of the major drainages on the south side of the Clark Fork Valley between here and Trout Creek, more than 30 kilometers to the southeast, have similar deposits. Now, what's the problem here? Well, the problem is, if you go back and you look at a map here, whoops, where was that map? Back up. There. The outflow of the lake, the draining lake. So let's say here's the ice dam breaks. Your outflow is from east to west, right to left. But what these deposits are showing is megafloods flowing west to east. Get it?
Yeah.
Something's not adding up here. And this was something this is why I had this paper. I'd probably read it, 5 to 10 years before I made my first trip. And I knew I had to look up Breckenridge because this whole thing, I'm going, okay, so this is not adding up. Something is contradictory here. Unless, of course, those flows were created by water flowing into Lake Missoula from the Purcell Trench. See? Now, I still haven't figured out how they fit within the whole sequence, but I think that would be an important thing to do. These are huge currents coming from the right, coming from the northwest, flowing southeast, flowing into the Clark Fork Valley in the direction opposite this presumed flow out of the valley, which would have been the draining Lake Missoula. And there's, you know who that is?
Graham?
Yeah, that's Graham Hancock. I wanted him to see this so that he would know that there's field evidence that just is not explained by the standard model, if you want to call it that. So here's the mouth where the Clark Fork comes up and discharges into Lake Pend Oreille. So this would be the outflow from down here up this way. But these deposits are showing massive currents flowing in this way. The ice dam is presumed to have been a sublobe of the glacier filling the area of Lake Pend Oreille and extending up the Clark Fork approximately to the dashed lines. Now, I don't know if you can see them. Here's a dashed line right here, and here's one right here. So if you look carefully, you'll see that I've taken this transect is in a constricted zone, and this transect is in an open basin. Okay? So I'm going to show you this cross-section in a second here. The exact position of the glacial terminus has not been identified. The two section profiles are shown in the next 4 slides. So here's northeast to southwest transect at the western entrance to Cabinet Gorge, about 8.5 miles east of the Montana-Idaho state line. Approximate location of the ice dam. So go back. That is this dashed red line right here. Then we have this dashed red line here, which is where the channel goes from a constricted channel up into a wider basin. And so now I've put in the high water level, 4,200 feet above sea level. And then I'm putting the Empire State Building in just to have something to kind of gauge the scale. And then where the transect in the basin is here, it's still going to be 4,200 feet above sea level. And then I put in the skyline of Atlanta. So this could be any major urban area in the world. And this gives you a sense of the magnitude of these flows. And there's Lake Pend Oreille. Has a monster in it. So here's Victor Baker's paper in 1992, Magnitude and Implications of Peak Discharge from Glacial Lake Missoula. New field evidence and discharge calculation procedures provide new estimates of maximum late Pleistocene Glacial Lake Missoula flood discharges for 2 important reaches along the flood route. Within the Spokane Valley, near the point of release, the peak discharge would probably exceeded 17 plus or minus 3 million cubic feet per second. So we can put in probably exceeded. Okay, so let's add 3 million, go 20 million cubic feet per second. 20 million cubic feet per second, okay? So that works out to be 20 million cubic feet per second. So I'm going to divide that by...
Cubic meters per second, no?
Cubic meters, sorry, yeah. 20 million cubic meters. So in a cubic meter, there's about 36 cubic feet in a cubic meter. Okay, so I'm going to go 20 million, 20,000, 1, 2, 3, times 36. Let me do it again here, sorry. 20, 1, 2, 3, 4, 5, 6. 20 million times 36. So that comes out to be 720 million cubic feet per second. So remember I said some of the largest floods in modern times in North America was like the Great Mississippi River Flood of 1993, which peaked at St. Louis, Missouri at just over 1 million cubic feet per second. So we're looking here
Pales
at
in comparison.
Yeah, 720 times greater than the greatest measured discharge on the Mississippi River. What does that mean? Can we just say, oh, well, it's just we can just extrapolate upwards,
It's just same thing that's happening, just at a different scale. Scale doesn't matter, though.
So, yeah, peak discharge, this is what Randall says, if you want to believe anything that guy says. A peak discharge of 17 plus or minus 3 million cubic meters per second means that flows were somewhere between 14 and 20 million cubic meters per second. A peak flow of 20 million cubic meters per second is equal to, I rounded it off, 800 million cubic feet per second, or about 500 times the volume of the Mississippi River during its greatest historical floods. Okay, so yeah, it said it would top out a little greater than a million cubic feet per second. And then you can see some of the handiwork of the floods. This is backwash. And, when you get to these guys, when you realize there's stuff like this all over the world, yes, all over the world. I would say to somebody like a Flint Dibble, when he's so convinced he knows everything that happened more than 12 or 13,000 years ago when it was nothing, basically. And he's always, they're always asking the archaeologists, well, where's the pottery? Where's the evidence? Where's the rusted car bodies, I guess, whatever they're thinking. But what I would say is, you look at this, and I would say to somebody like that, how do you know what's in that deposit right there? If this deposit's from 13,000 years ago, where did this stuff come from? Well, this stuff was prior to the flood that put this stuff here, or floods. This was part of some bedrock somewhere. It might have been the floor of a valley. There could have been a village. There could have been a whole city in that valley. I just showed you the cross-section there of Clark Fork with a whole urban area for scale. Right? After that water passage, what would you find of that? Nothing. It would have been reduced to rubble. It would have been reduced to gravel. And what are we doing to build our modern civilization? We're quarrying the gravels, the immense gravel deposits that were left behind after these cataclysmic floods. So we're literally building our new modern civilization out of the wreckage of the former world. Literally. Houses built upon unstable flood gravels. This was dumb. In fact, I think the last time we drove by, these houses weren't there anymore. Yeah, note bedding layers. But yeah, this is dumbness.
Yeah.
So, I suppose we should terminate. How long have we been going?
3 hours and 15 minutes.
Well, this is probably enough of an episode, but I would like to conclude with one thing. I will stop sharing. And this is going to be quoted from a book by George Catlin. And George Catlin was an artist who spent many decades traveling amongst Native Americans, living with them, hunting with them, and painting them. So this is from a book. Let's see, this is 320 here. Let's see. So this is page 320 within the book. And the book is called, let me give you the exact title here. You can find this online if you want to read it. So the title of the book is Last Rambles. Let's see, Last Rambles. Look up George Catlin, Catlin, George, and then put Last Rambles. Here we go. It's finally loading up.
Last Rambles amongst the Indians of the Rocky Mountains
and
the Andes.
Yes. Okay, so he had something very important to say, and just extremely interesting. let me go back to where I was. Let's see, 300. We'll just go back to about page 320. Let it reload. And I'm going to quote from his work. And it has relevance to all of the things we've been talking about here. Okay, he says, the American Indians are as distinct from all the other races of the earth as the other races of the earth are distinct from each other. And both in North and South and Central America exhibit but one great original family type, with only the local changes which difference of climate and different modes of life have wrought upon it. And then he goes on to say, I believe they were created on the ground on which they have been found, and that the date of their creation is the same as that of the human species on other parts of the globe. That's very interesting, because nobody believes that today. This belief is founded on the reasons advanced in the foregoing chapter, supported by the traditions of the Indians, which will be noticed, and a strong and unavoidable intuitive disbelief that all the races of man of different colors have descended from one pair of ancestors, involving from necessity the crime of incest, which apparently would be implied. So then he goes on to say this. I'm going to skip a few parts here. Indians are the descendants. Let's see. He's questioning the route by which, if the American Indians, now remember, this is written in the 1800s, if they are descendants of Adam and Eve at the rate that an infant savage population would spread over an uninhabited and desolate country, several thousand years would have been required to populate and move through the vast regions of Kalmuck, Tartary, and Siberia to Bering Strait, a distance of more than 10,000 miles, and from Bering Strait to Central and South America and Tierra del Fuego, 10,000 miles more. So he's talking about, and this gets us right into the discussion of where did North American inhabitants come from? When did they get here? And questions which have not been have not been resolved yet, right? Now, we can go directly to the traditions of the native peoples themselves, which he does here in his book. But I think the point is that he's making is the difficulty of traveling such a great length and distances in a short period of time. And an equal time required, 1,000 years at least, for a civilization to arise sufficient to have built the splendid monuments of Yucatan, and the vast space of time that has transpired since those monuments were depopulated. In all, a space of time far transcending that allowed by sacred history or even by geology for man's appearance on the earth. Now, this is where it gets interesting. The American Indians know nothing of this, yet their traditions and monuments prove beyond a doubt their great antiquity. For of 120 different tribes which I have visited in North and South and Central America, every tribe has related to me, more or less distinctly, their traditions of the deluge, in which 1 or 3 or 8 persons were saved above the waters on the top of a high mountain, and also their peculiar and respective theories of creation. Some of these tribes, living at the base of the Rocky Mountains and in the plains of Venezuela and the Pampa del Sacramento in South America, make annual pilgrimages to the fancied summits where the antediluvian species were saved in canoes or otherwise, and under the mysterious regulations of their medicine or mystery men, tended their prayers and sacrifices to the Great Spirit to ensure their exemption from a similar catastrophe. Indian traditions are generally conflicting and soon run into fable. But how strong is the unanimous tradition of the aboriginal races of a whole continent of such an event? How strong a corroboration of the Mosaic account. And what an unanswerable proof that the American Indian is an antediluvian race. And how just a claim does it lay with the various modes and forms which these people practice in celebrating that event. How far these general traditions of a flood relate to a universal deluge, or to local cataclysms, of which there have evidently been one or more over portions of the American continent, or whether there has been a universal deluge and at what period, it is difficult to determine. One thing, however, is certain. The Indian traditions everywhere point distinctly to at least one such event, and among the central and southern tribes they as distinctly point to two such catastrophes in which their race was chiefly destroyed, and the rocks of their countries bear evidence yet more conclusive of the same calamities, which probably swept off the populations in the plains, and as their traditions say, left scattered remnants on the summits of the Andes and the Rocky Mountains. That's worthy of a for sure.
What a story that we have unfolding here. So we've looked at the mass destruction that this has caused, and we've investigated where it may be coming from. And next time, we're going to talk about, hopefully, what may have caused this mega flood.
Well, I think we may have to actually be talking plural.
Mega
Now,
floods.
notice that it did say that a lot of the tribes in Central and South America thought there was two.
Yeah.
And, of course, what does the old priest tell Solon? Well, you Greeks only remember one flood. There have been multiple gigantic floods. Yeah. So there's a lot to unpack here. But we're on the trail of something, and I think I can say with assurance that the resolution to this story has not been solved yet. There's still a lot of pieces that have to be put together. And once we can get out of this straitjacket of uniformitarian, gradualist type thinking, I think we'll be in a position where we can actually begin to come up with an explanation. But two things: break out of the straitjacket of models and thinking, and also expand our thinking to a wider domain. So yeah, we can pick it up if you want to do this next time. We'll pick up this story and see where it goes. And I think we could possibly hone in on a solution.
I love that. Let's do it.
Okay.
Until
You're
next
on.
time. Salute, Randall.